Yeah, welcome everyone to the first OPI Summit on DPUs and IPUs. I'm Sridhar, by the way. I'm Sridhar from Linux Foundation. I'm the project manager for the OPI project. Uh, so we will just a quick logistics information for those who are joining virtually, right? For them to see the content. If you're a speaker, you have to just join that Zoom meeting. Just put the meeting ID and password on the board. And just share your slides so that those who are joining virtually, they can see the slides. So sorry for the last minute inconvenience, but that would help for those who have joined to see the content. They can hear the audio through this mic. Just to see their slides, you need to join to the Zoom and just share your slides. That's the first request. Um, then that's all. I think let's get going. I hope you all got your breakfast and you're ready to start the sessions. First, we will start with our governing board chair, Venkat Pulela, the CTO, Tech Networking at Keysight Technologies. I think quite a few would be knowing. We will start with a quick introduction to OPI, what it's been doing, what it's doing now, and what it will be doing going ahead. And let's get started. So Venkat, over to you.
Thank you. Good morning. How many of you were at OCP? All of you? Okay, so good attendance. Okay, so let's get started with OPI, where we were, where we are going. It's good to just kind of recap. It'll be a little bit of an introduction to what is OPI, because some of the folks are joining. Some of you are well aware, you're part of the journey, you built it, so you're aware, but we have few folks who are joining from elsewhere. So far, in the interest of, in their interest, let's just recap a little bit. Okay, can we check if the audio is available for the folks on the Zoom, right? Yeah. Before we get started, thank you. Thanks our premier members, ARM, Dell, F5, Intel, Keysight, Marvell, Red Hat. These are the folks who are paying the bills. Really appreciate that. This is a very important initiative. DPUs play a big role in terms of how our infrastructure is evolving. And we have your CPUs and GPUs are very clearly positioned where they are, what they do. But quite a few people are confused about DPUs, IPUs, you know, what happens there. But, you know, some of these companies are seeing the potential and then the value that they can bring. And appreciate that. And also general members who are part of the community. Thank you. So what is a DPU? It is, we have seen it, again, I mean, we spoke about it multiple times for somebody who is joining new. It is an evolution of the NICs that we have. And then over a period, the NICs have become smart NICs, and smart NICs have become, you know, special. I mean, in the beginning, there is a NIC, and then there's a specialized NIC. Maybe they were doing one function, whatnot. They have evolved into IPU DPUs, which have enough functionality to become an independent system, right? But they're also, in terms of form factor, they are sitting in between your network, which is your backbone backbone to you know, a server network, right? And the server side itself, it's growing, and it's typically has, you know, a few ports, not as many as your switch, but this is your entry point into your server or into your system. They have their own independent BMCs, and the unique thing is that they have a bunch of cores that are flexible cores that can really add compute, and then they also have a bunch of accelerators. How do we combine all of them and provide value to the host, as well as the traffic that is going from the host to the net, right? So that's where they do, and uniquely the number of flows for these hundreds of gigs that are hundreds of gigs speed ports that we have, it's very difficult to scale in a central location. If you have a switch, they're really good at header processing, but when you really want to look at flow processing and you want to go deep inside and start doing services, they don't scale well. So that way DPUs have formed a nice form factor which can accelerate those services. So that's what it is. In terms of system architecture, right, it has definitely evolved from how a NIC, even with a lot of functionality offloads, was still part of the server or the system, and then it's almost looked at as a peripheral, right? Whereas with all the capacity and capabilities, they are with DPUs and IPUs, it clearly evolves into its own independent system. And in terms of architecture, that is the biggest change. And then that brings a unique value, because imagine a server with a bunch of these DPUs. It can take an appliance form factor. If the same thing goes into a switch again, it becomes part of the network. So on both sides of the wire, on one side it can be part of the host. In the middle, it can become an appliance. If you put it on the other side, it can become part of your infrastructure, becomes smart switches and smart TAR. So in terms of manageability, in terms of system architecture, that's the evolution basically. And when we started, our goals were really to how do we build a community around standards-driven ecosystem, right? Idea is not to come up with something new. If we find anything out there already, we don't want to reinvent. We really want to take that and extend and use and collaborate with those groups. That's the biggest goal. But from the beginning, we want to be vendor agnostic, because the biggest challenge is that all the hyperscalers and the larger companies with some of these who pioneered some of these technologies, they all have gone their own proprietary ways because of the speed of innovation and for various reasons, right? Their business speed of their business and whatnot. But the idea is that, how do we unlock the value by bringing it out when in a vendor agnostic way as a community? Okay, what is that we can design as an industry-wide co-design with common APIs and move fast. So, and our goal is also how do we build some implementation examples that we can share and that will help somebody who is adopting this quickly, right? And then why you should care about OPI is because, the largest companies, they already have the movement. I think definitely there's a lot more value for tier 2, tier 3 players is where one way to look at it. And any non-standard framework does not unlock the value, or even if it unlocks, we don't get that multiplier effect. So that's the biggest goal for us. And then to drive a broader adoption and kind of get into a positive cycle, I think OPI is key. And anything that you do it as a community design, collaborating with everyone else, we will be able to accelerate the adoption as well as bring out the value much faster. We have a bunch of demos that's already out there. There's a link here, go there, take a look at some of the demos that are already built. And going forward, our priorities, ideas, of course, we want to continue to do evolve the APIs that we have. But idea is also to look at solutions as set of blueprints that somebody could adopt quickly, right? Instead of looking at them as features, a set of features that are kind of aligned would get us going much faster. The operating structure, some of you who are new to this, we have a board, we have a technical steering committee that's guiding us in terms of how do we things. There is an outreach committee that is guiding in terms of how, including this summit, how do we engage with others, how do we get the word out. And actual work is done by 4 working groups. Again, we want to really we want to be driven by the use cases from the customers. I think that's what is going to be key for our success going forward. And there are a couple of QR codes that you can use to access some of the resources, right? And call to action is, participate, talk to folks around you, talk to your customers, talk to, even if somebody is there who may not have a solution or cannot contribute, I think even use cases are very useful for us, right? Find your customers who have a need for this, who could benefit from it, bring them to OPI, and we are willing to listen. We want to, take their feedback and what would make this useful for them and go it from there. And of course, join the working groups, get resources internally, get your engineers to, participate and in the working groups and go from there, right? Thank you again, and then welcome. I know it's hard to get up early in the morning after the 5 days of getting up for OCP and coming here, but good to see all of you. Welcome. Thank you.
Do you have any questions? Hey, thanks a lot, Venkat. If we can take you. Our next session, we have Balas Nimit from Red Hat. So he's a senior principal software engineer at Red Hat. Do we have Balas here? So he's one of our very good contributors at OPI. He'll be talking about OPI from the future is, I think he is mainly focusing on the work that they did together, and OPI APIs from vision to reality and a call to action. He had presented, I think, those who are not familiar with not joining the OPI TSCs, he had presented 2 talks around the APIs, one in like March of this year and another in August, September this year, I believe. Yeah. So I think if you hadn't attended those talks, I think he will summarize this thing and present. Thank you. Thanks.
Slideshow. Hello? Yeah, okay. All right, so this presentation is going to be a little bit different than the one I did in March. So if you didn't see that one, I'll try to tie into it. Because today I want to actually show you some things that are working. I think that's more interesting than just talking about slides. I think OPI needs more terminals and more code. So I hope I can bring that. All right. So starting with the why, right? We're creating this foundation for the unknown, right? Because everything that we've been doing has been, let's say, difficult because nobody knows how to use DPUs. When you go to customers, the first thing they say is, oh, it looks good. And then we ask, how would you use this? And they say, we don't know. So we're trying to figure out how can we build this foundational platform that can be used for anything, right? So because we don't know that killer app, we just want to have this infrastructure ready so that if the customer sees how it all fits together, they can start bringing their own workloads and we can start seeing how the next step would look like, right? So the bottleneck is it's hard to manage these things. So as many of you know, you bring in this new DPU, or you're a vendor, you bring in this DPU, and it's hard to manage. You need to ramp up on all the vendor-specific details. You need to read a lot of documentation, and every card is different. This has been the huge pain point, right? So the solution in OPI is, yeah, let's build this vendor-agnostic environment, open, and any workload can run on it. That's the goal, right? So we're focusing on offloading first, and then acceleration. That's by design because we've seen this in the past. If you mingle those 2 goals and you try to do offload and acceleration at the same time, you will not get very far because it's just too much. So again, building that offload first as a foundation and then focusing on acceleration next. And then once we have all this set up, we can then bring in the developers and say, okay, these are the APIs. If you're using these APIs, you'll be able to leverage all these other DPUs, right? Same from a vendor's perspective. If you're a vendor, you're coming in, implement these APIs, and you should be good. You join the ecosystem, and as a, you join the ecosystem, and then as you're building new applications, you can also just use what's already there without having to reinvent the wheel. Okay. So recap of where we are. So phase 1, it's really complete from my perspective, right? So we've successfully defined what is the minimal set of APIs to get anything working. We've been here for quite a bit of time and we're past that phase. We're now in phase 2, real customer adoption. So we're running the first trials at customers, no longer real proof of concept, but actually developing real world use cases. And the goal is to then have actual tangible value, not just the promise or a potential. So I think demos speak louder than words. So let's just jump right through it, or in it. So a lot of things can go wrong here, and I think that's part of the excitement. All right. So I am VPN'd into our own lab. The intent was to deploy what you're going to see here in the OPI lab, although there were some difficulties with hardware that prevented us from doing it. What's important to realize is there's nothing technically gating us from moving what you see here into the OPI lab. I'll talk about that later as well. So let me first go into the directory. And I'd like to also bring a diagram into the picture. So the first thing I'm going to do is make sure that I start with a clean environment, because this is actually a live environment, so I don't want to break the demo because something else has been running. And what we see here is a cluster, right? So in the end, we have the OPI APIs behind the scenes, and what you then build on top is an implementation in OpenShift or Kubernetes. Like OpenShift is the Red Hat version of Kubernetes. So at the top, you can see a bunch of nodes, and on the bottom, you can see DPUs. So let me zoom in. So at the top, you can see 3 master nodes, just like any other normal cluster, 3 master nodes. That's what you see here. And then you have 3 worker nodes. And inside each of these worker nodes, you can see a DPU, right? So if I go back to the diagram, 3 worker nodes, that's what I'm showing here, x86 servers, and then 3 DPUs, okay? And everything is working in one environment. What's important here is that we're talking about an IPU, an Intel card, a Marvell card, Octium 10, and Phantom Lake. So 3 vendors all in one environment, seamlessly integrated, right? So within this whole infrastructure, there's a lot of other stuff going on. So it's useful to have the user, to give the user the ability to see what the state is. And so you have a command called OC-get DPUs. So this is, if you're familiar with Kubernetes, it gets you custom resources, gets you information, and you can see all the DPUs that it's detecting. So you see 6. Why do you see 6? Well, what this is telling you is that on each server where there is a DPU, there's 2 sides. So there's the card, and then there's the host side, and we're running a piece of software on each side, and they're looking at the hardware. And so each one of these, you see it twice, because on one side is the DPU and one side is the host. So it's as simple as that. And we give them names, a unique identifier. We can figure out how we want to display this, but just for the sake of the demo, it's a unique identifier. And then you can see what kind of DPU you're talking about, and the state being true. So depending on the DPU, it might be in a healthy state or not so healthy state. So that's what you see here. So in more detail, let's continue. So behind the scenes, there's a bunch of components running to get this working. And if you go into the namespace, I hope this is big enough. If you go into the namespace that contains all these components, you'll see that you have a bunch of DPU daemons. That's a component running, again, on the host and on the DPU. So that's what you see here. And on each of the different sides, right? So these things are making it so that everything is managed seamlessly for you. And all these components are using the APIs, the OPI APIs, right? And then we have a controller, a network resource injector. Those are all details, not so important, although these are important. So the VSPs, the vendor-specific plugins, of course, since vendors have particular ways of managing DPUs, we need to put that detail somewhere. So we put it into what we call a VSP, we hide it away, and from a user perspective, you don't even need to know about this, although the system needs to recognize that which DPU is running where, and it needs to start those components so that the hardware is managed. Okay, so next let's start a demo. This is where it will become a little bit more interesting. So we're going to first do some cleanup, and then we're going to start a pod on the Marvell card, and I start a pod on the Phantom Lake. So what's important here is that from a user perspective, you're literally using standard Kubernetes primitives, right? You're applying a YAML file and not yet another YAML file. And then what you see is you get 2 pods. So if I run this again, as I was talking, it had enough time to make sure that those come up. So in this environment, now you see 2 pods in the default namespace. One is running on the Marvell card, one is running on the PTL, on the Phantom Lake. That's what you see here. Each one has an IP address. So you see, that was as easy as it gets from a user perspective. Behind the scenes, a bunch of OPI-related things happening. So now we can create more pods. And, or is this the same? Yeah, it's the same. So what I'm going to do next is I'm going to create the deployments. So on the host side, going back to my diagram here, I showed you that you were able to create these 2 pods here, right? I'm now going to create a deployment on the host side, and it's going to create some pods on x86 and some of them on this other x86 node, all plumbed into the data plane. So if I create this, going back here, so we get 5 pods. And every time I run this demo, it's a little bit different because Kubernetes scheduler will figure out where it makes sense to run these. We have constraints like we need the DPU devices and we need like particular labels, but otherwise the scheduler is free to run it where it wants. And we see that it ran it 3 times on the Phantom Lake and 2 times on the Marvell card. So if I get this again, so now all of these are running, and that means that it's plumbed into the data plane, going through either the Marvell card or the Intel card. And the only difference here, and that's what I want to point out, is literally, of course, a different name, but only this is the real difference here. We're just selecting a different device. It's really emphasizing the fact that these are industry standard commands. Everything is green. Let's just double check that everything is working correctly. Yeah, so we did that. And then we'll look into the IP addresses. So inside of the pods that are running on either card, we'll look at the IP addresses. So that's what you can see here. These are shown here. And then we're going to show that ping actually works. So because everything is now integrated into this like unified environment, all these pods can talk. And that's important, right? So this pod can talk to this pod can talk to this pod can talk to this other pod. Every pod can talk to each other, right? And this is really the power of when you have OPI, right? Because if you would have a vendor-specific solution for a particular card, that card would probably be able to talk to the same card from the vendor, but not to a different card, right? And because we've unified everything, everything can talk to each other. Okay, and then I'm going to show that, yeah, there's more ping examples here. So this is going from the host to the card as well. So that works as well. So you can look into the details, but the gist is really that everything can talk to each other. So if I now, instead of using a simple workload, let me just clean this up. I'll start using Nginx instead. So since you have this diagram here, the blue pods here, those are just normal pods. That's important. So we can switch out the pods for something like Nginx, right? And so I'm going to show that now. So this case is going to deploy it on the Marvell card. You see it's also pretty fast. So skip all of this. I think what I can do here is deploy this one straight. So we're going to deploy the Nginx pod. Takes a while because it's configuring the IP addresses as well. Might have skipped too many steps. Oh, it's ready. So Nginx is now ready. That's good. And if we actually check the deployment, you can see Nginx is ready. And then in this case, let's check where it's running, because we did use selectors to force it to run on a particular DPU. In this case, it's running on the Marvell card, right? And then we can, yeah, so that was good. Then we can run a demo to do some kind of workload. And I think the next presentation will talk about that more. Although, because we're doing demos, sometimes things go wrong. So imagine that this worked, because it did earlier today. So that's all good. So clean up, and we're going to move that to the Phantom Lake. And again, the only difference is literally the node selector. So we select it to run on the Phantom Lake instead. So it's now coming up on that Phantom Lake card. So now we ran it here first, and we moved it here. Hopefully. So let me just run the cleanup first. Hopefully I can get this working. And then run it from here. Yeah. And again, let's have a look. Those are the nodes, and let's look at this one in particular. So you can see now the Nginx pod is running on the Phantom Lake, and hopefully we can do this part where we do some kind of prediction. So this is actually going through that Nginx pod and to the host on that side. Okay, so that this works pretty nicely. I have a stretch part of the demo. Hopefully we get to that at the end, and maybe we break the cluster, and that's good information to have as well. So let me go back to the slides. So this is what I've demonstrated now. One cluster, multiple DPUs in the same cluster, working all seamlessly, minus that bug. So how did we really do that? Well, there's a bunch of APIs. We have a discovery API. That one is doing like the discovery of the DPUs, identifying each of the DPUs, figuring out like, okay, what kind of capabilities do we have in the cluster? We have a health probe API. So if the DPU would go down, we get some information about that, because of course things can move, and from manageability perspective, we need to know. We have a provisioning API. I didn't demonstrate that here. That has been part of OPI for quite some while, but all those things have been deployed here with those APIs, right? And then mainly the networking API. So because we have this unified data plane now that builds an overlay across all these DPUs, everything can be managed in the same way. And this is really the power of that common standard, right? OPI. Complexity abstracted, operations simplified, because we're using standard Kubernetes primitives. So where do we go from here? If you look at the GitHub repo today, not much has been happening in OPI, if you ask me. However, what we want to do here is we want to take these APIs and we want to upstream them. So these APIs have been partially living outside of the OPI repo. We want to move them into the official OPI repo. Next one is getting hands-on experience. So today, what we've shown you is actually a pretty powerful MVP, and we really need those customers. So the intent is to move that environment into the OPI lab and get it into the hands of the customers and get feedback by asking them through surveys. Are we building the right thing? Can you start using this today? And if not, what is really missing still? However, since we've already seen that this is being used by some of the customers that we have been interacting with, we have a pretty strong opinion about what we've built, although some customers might want something else, so we definitely want to hear from as much customers as possible. And the next one is enabling more use cases. So the next use cases that we're looking at is Kubernetes FRR and Big IP, and aiming to implement both by adding a single API extension into what we've built. If you really think through this, both could be enabled by using multiple bridges, and this is also what we believe should be implemented next. And especially since some customers are explicitly asking for Kubernetes FRR, this is definitely one of the things on our roadmap. And then we want to extend the lifecycle management. So there are still some edge cases where if you reboot the system or you you kill some of the pods in the middle of the process, the system gets into this weird state. So we want to make sure that we can recover from all kinds of edge cases. The main focus will be, of course, on the Kubernetes FRR and the Big IP use case. And now this is really where I need everybody's help, right? So if you're a DPU vendor and you've not seen your DPU in that list, I really encourage you to implement those APIs. If you do, that means that we can take your DPU, add it into the same cluster, and build this bigger environment so that the customers that are coming can access this single point where they can see all the DPUs managed in the same way. If you're a customer, then this MVP is really for you, right? We really need your feedback because we need to break this cycle of we don't know where we're going. Is this what we need to build? The MVP is ready. Let's talk about what you want now. So if you're a network function vendor, right, like an actual application provider, then collaborate with us because maybe your specific network function wants to be wants the environment to interact in a certain way, and we want you to help us add it as a blueprint. So we want you to help us identify gaps and close those, and maybe extend the APIs so that we can get your network function into the same picture. And maybe you're just a general contributor, so help us define those next APIs. As of today, we've been collaborating with many partners, and we'd like to collaborate with more. So please help us, help with writing documentation and spread the word. And that's it. Thank you. Any questions? So that's a very good point. We support both. So for the sake of the demo, because it's a more powerful message if you can see everything in one page, we have the exact same setup with multiple control planes. So this is completely orthogonal to OPI, and that's a very important point. The APIs are almost below OpenShift or Kubernetes. They need to be written in a way that it doesn't force you to use one or force you to use multiple control planes. However, at the higher level, you need to use those APIs to implement whichever you want, and we support both. Anyone else? Yeah. Yeah, so I think the question is how we deal with security boundaries. Is that? Right, so from an OPI perspective, that's one part of it, and then there's Kubernetes as well. So from an OPI perspective, there's a single point that the components interact. So if you go back to my presentation from March this year, I think there's some of it is being answered there, but if you look here, there's a daemon running on this side and a daemon running on this other side, and both are connected through a gRPC. And everything goes through that single point. When we run in what we think is no trust mode, it's up to the DPU to listen or to ignore requests. Everything that the host side asks from a configuration perspective of the DPU is only a request. If you're in no trust mode, you just ignore the request. And if you're in trust mode, you can execute on those. And it's really at that point that you add all the security. All right. And? The switches actually, or like
SAI, Sonic and the Sonic interaction.
Between these two? That's a good question. I would need to think about that more. I don't think there is, but I need to think about it more. if there is a relationship between these and the Sonic and the SI implementation. And there was one more question, I think. So SCTP would be before all of this, right? Like this is already, I've spared the pain of having to wait for the deployment because of course installing servers takes quite a bit of time. And so SZTP, sorry, is coming before, right? What we're using here is we're using Redfish and PixieBoot, although OPI has the zero-touch provisioning APIs, and they definitely have a place and we need those. But those are come before the actual deployment, what you've seen.
Defined by Sonic network. We looked at other approaches as well, but Sonic was definitely. In that case, DPU was assigned to that Sonic instance. And we did not ultimately go that way. That wasn't a general enough answer for requiring DPUs, but it was discussed. And it was discussed extensively about 2 years. So this was one of the first discussions we had in the API working group. If you go back to those early decks, you'll see a lot of discussion about P4 packet forwarding, P4 packet forwarding, Sonic, and what should the networking API look like for a DPU. So that there was extensive discussion early on the people, the people on the API working group. Now, the analog to SI on a DPU was also discussed, and we never really closed on that, right? I mean, the API group danced around that one a few times and never really closed on it. But you wouldn't use SI as SI unless you were going to put Sonic. But forcing DPUs to look like little embedded switches was an interesting idea that didn't pan out in the end. It was.
Yeah, so what I would like to add here is we're really opening up the DPU, right? It's like you can, and that's really the emphasis here. It is just another pod. If you want to do something specific, for example, if you want to use P4 acceleration, it should be part of that pod. We're not saying that you shouldn't do it. We're still building this environment, and we're seeing some customers are asking for that because they want to leverage some kind of specifics for the hardware. What we're built here is we've pushed out all those choices, all those decisions, so that what we built is actually usable today. Keep it as open as we can, and maybe OPI is just about this and not more. Like any piece that we decide on makes the future more defined, right? So if we define, let's say, at the OPI level that we want to do some kind of layer 3 firewall configuration, then that API becomes tied to that particular layer 3 implementation of a firewall. And this is the risk, right? Like initially, very early on in OPI, we've seen huge APIs that were defining all the possible things that a networking could do. And we felt like that is the other extreme, right? And it would tie us very much into what can be done at that point in time and not so much build this open infrastructure. And I think that ties into what you're saying as well.
Yeah, so it was, again, you could imagine doing that, but and you could imagine making it future forward looking. I mean, SI and Sonic are certainly that, but it's an enormous amount of work. And Dash kind of took that approach for their gateway offload. So there's a parallel project called Dash, and it was trying to define functional models for essentially network gateway translations as an adjunct to Sonic. And that's So if you also want to look at another approach to how to break down APIs for these things, we pivoted to trying to get the platform and core infrastructure and what I call bring up APIs common and correct. And that's what was shown here today. And that's largely worked because that stuff really can be common and is straightforward enough that, but still provides value that you could do it with a modest effort. So there's certainly a lot of opportunity to have more complex, higher level APIs and more complex APIs for additional functions, but we would need a demonstrated desire for that to actually be done in common. So, and that's the wall we kept running into with early OPI, because we started with a grand vision to have, all singing, all dancing API across everything. What actually came out is very useful. This has been shown here, but just as a kind of a high level framing to follow on what Venkat was showing in this presentation.
Hey, thanks a lot, Balash. Now we go beyond API. I would like to invite Vijay, Senior Principal Engineer at Marvel, and Paul, Principal Architect at FI. So they'll be talking about going beyond API, building a production-ready network function ecosystem for OPI.
Yeah, hi everyone. I'm Vijay. I'm from Marvel, and I have originally joined OPI meetings at the very beginning, so I recognize some of the names here. But later I was like not participating much. So today, me and Paul are going to talk about how we move forward from what Balas has presented. So in fact, we are working together, Red Hat team, Marvel team, and F5. We sync weekly on this. So it's the same talk actually. We don't want a very big talk to and bore you guys. So we have broken it. So it's like a continuation of his talk. We will go little south from what he has presented. And then we will talk about two NFs which we have packed, which are like deployed with OPI compliance and also configurable also with OPI APIs. That's the talk. And I'm going to cover the initial slides and I'll ask Paul to join then for the Nginx part, right? Okay.
Sure.
You want to say something?
No, I'm good.
Okay.
So
Okay, let me start.
I'll introduce myself.
Yeah, okay. Yeah, so basically this is like continuing of what we are doing. What Balas has explained is like how we are deploying the OPI compliant functionality on the DPUs. And I want to start from where we have started and how we collaborated and why we collaborated with Red Hat. And for what aspects we have looked at OPI and how we are leveraging OPI to actually make a really production grade usable solution. That's where we are right now. I just want to cover the journey, like how we got there. Okay, so this is where we have started. So this is Marvel's IPsec solution. So as you can see on the DPU, our stack is built on VPP. It's open source VPP, and we have a plugin which is part of like VPP. It's a VPP plugin which is also open source. So when you use this plugin with VPP on an Octeon card, it leverages all the hardware functionality there. So this is like you get line rate crypto performance with this solution, and it's already used by the customers. It's already deployed, right? So, but there are like, so even though this is like a performance-wise, it's a very good solution when you deploy it as a monolithic application on the DPU. When you want to bring it to cloud-native environment, it has like quite a few issues, right? So one is there is no lifecycle management. We cannot launch and recycle the application on the DPU, which is our VPP, in a cloud environment, right? Like it's like done very statically. So we launch the VPP, and that's it. Like it's a one big application which connects to all the ports which are towards the host side. And then you don't know which ports are connected to which apps on the host. So then you have to manually do the mapping and then send the traffic so that it comes to the right ports and do everything manually, basically, right? That's the second pain point, right? The VF mapping is very tough and it's very static. You cannot allocate and recycle resources dynamically. So that's the second problem there. And then we have, so once you do all that, like how Bala showed, like how you launch things, and then you have the other problem, like for any standardized application, how do you configure it? So there should be like a standardized way. So with VPP, if your data plane is VPP or XFRM, you have to log into your DPU and maybe use VPP CLI or use Linux shell to actually configure your security policies. There's no other way, right? So there are some workarounds for that, but it's not really there. So as a first step, we implemented, before even collaborating with Red Hat, we actually simply implemented, to move to Kubernetes environment, we simply implemented a SRIOV CNI for Marvel. So we just get a secondary port, which you can connect to DPU, but the story ends there, right? Like the port is there on the DPU, but then it's like you have to still do the manual plumbing, connect to your data path, and then configure it. All the other problems remain the same, right? So this is the work which we did with Red Hat. So this is the DPU operator. There are like so many components shown here. I think Bala's covered few aspects. So I want to cover some other aspects which he didn't touch on. Maybe he did it in the past sessions, I don't know. So basically, for the problems which I just said, like you launch a VF at the beginning on the user pod, and then that particular VF, you have to send it to that information, you have send it to the DPU, right? So for that, we have all these components which actually pick up which port you have connected and send that port information down, and then you add it to your workload, which is your, in this case, IPsec application. I'm taking IPsec as an example, but all this discussion equally applies to something like Nginx, which we will talk about later, right? And then you have to do the plumbing in the on the DPU, like how you connect that particular port to direct the traffic to your NF. So we implemented in a very generic way. So there is a programmable data plane here. It's right now based on OVS. And you can actually link more than one network functions. Let's say you have load balancer and then IPsec. You can actually link both in this scheme. Right now the facility is there. So we worked on this with Red Hat, and we also developed the vendor-specific, basically Marvel-specific plugin for this. So this is like one step which we did, and then we have this other problem. Like now you have your IPsec loaded. Maybe I should hold my mic closer. But you still have the problem of like, how do you configure your IPsec? So you still have to log into your NF and then configure it. So that's where we turned into OPI. So we leveraged OPI for this third problem. So we use the OPI bridge concept. So I'm assuming most of the people here are familiar with OPI bridges, but I'll just have a brief. So it's not like what it sounds like. It's not really a bridge. It's just a translation layer from your gRPC, a common standard gRPC layer. You implement the southbound of it to every vendor implements in their own way. So there are like different bridges for different groups of applications. So storage, networking, and security. So we will be talking about storage because I'm demoing all this with IPsec, right? So this is how the XFRM, the strong swan bridge works. So you get a gRPC client, which is like, you can say OPI compliant bridge. OPI compliant entity, which is outside. It's a client here, which is given by, so this is like OPI code we used, but it could be like a security orchestrator using the same APIs to talk with the strong swan bridge. So the strong swan bridge in this case talks with strong swan using wiki message format, which is also pretty standard thing. So then once strong swan gets the OPI message, it actually exchanges the keys with the other end, and then it basically programs your data plane. So that particular programming of the data plane, there are like multiple ways. So OPI recommends that you have a plugin inside your strong swan to actually pick that information and program your data plane, like however you do that. So at Marvel, we have like two ways which we did it. Like we have two solutions. So basically, we created like two network functions for doing that. So if you see the left one for VPP based data plane, we actually snoop the XFRM information using a plugin inside VPP, and then it configures the VPP. So basically, the VPP solution which we talked about earlier can actually leverage this solution from the external configuration till the hardware. So VPP anyway offloads to the hardware, right? Crypto engine. So you get the same line rate with this solution. And the right side one is the other one where we use XFRM offload. So we let the strong swan configure XFRM, and we install the crypto driver on the Octeon, and it actually offloads the crypto part. So the difference is that here it's only doing crypto offload. The left side one is like complete IPsec offload, right? So I'll go over a demo now. So this is the demo setup. So we have just one node. So in the earlier demo which Bala showed, you have like multiple nodes in the cluster. So this is also same cluster. The only difference is like in their cluster, they recently combined the DPUs and host to the single cluster. But in this, it's different. That's the only difference. So the DPU here is running Microshift, and the host is in the OpenShift cluster, basically Kubernetes cluster, right? So you have this OPI client at the here, which is external entity, and we'll see how things are launched and how OPI client configures things so that IPsec, the configuration goes through all the way till the hardware, right? So let me. So I have a recorded demo for this. So don't worry about the time. I have actually a small cheat sheet to actually go to the good parts of this. It's a very long demo. The reason we created this is like the intent is to actually add this demo to the OPI demo folder so that it will be easy. So that's why it's very elaborate, explaining every step with some comments and things like that, right? Okay. Right. So here we are launching. So basically, I have like different tabs at the top. Like the DPU operator is the tab which basically you are launching all your pods, like the pod on the host and also the NF on the DPU, right? That's the beauty of this. You launch your actual user pod and also the related workload, and the plumbing automatically happens. So that's the crux of the solution, right? So here we are launching both. So the SFC pod is the one which is the IPsec NF, which uses OPI APIs, and the host pod is the pod which is running on the host, right? So, and then I go to the just showing that the pods are running, and then so this is the external test system where we launch a strong swan agent there. That's the guy who talks with the basically the data plane testing. So that there you have one pod there. So I just want to see that there are no policies, right? It's all empty now. It's blank. And then we go to So same with the launched IPsec OPI NF. So NF is also empty. So now we have set up things that we have launched a user pod and a offload pod on the DPU and the external entity. So the traffic is going from the external entity via DPU encrypted and out to the outside system, but the configuration is all empty. So now we can use OPI client to actually do all the configuration from outside. So for this all the way I will. So it's actually showing a lot of route setups and things like that just to show how things are working. So I'm skipping all that. So this is the OPI client. So we just run the OPI client from here. It sends the OPI message to your strong swan bridge, which is running on the NF, and it does the configuration. Right. So you don't need to log into any of this. So this can be done by your cluster security orchestrator logic using the same API. Right. And then I skip. Right. So now we are actually seeing that the configuration is done on both the systems. On the NF and also the external test system, both have the configuration created by key exchange. Okay. Yeah, this is on the NF side, right? So now we can do the actual send some packets and do some testing things because things have set up. Okay. Okay. So we're just checking the hardware counters on the DPU before sending packet. Did I pause it? Okay. Then we will set up all the TCP dumps everywhere just to see that, and then all right. Right. So that's the main test, right? So and we can actually see that it's done by DPU hardware, right? Connecting like the total north to the actual configuration. Okay. Right. So let me go back. Right. So that's the main goal actually, like leverage OPI to actually convert our existing production grade solution, which is like OPI compliant, so that the users can easily replace that with the other one. You have the launch, plumbing capability, and configuration capability all with that. So we have two NFs like that, which we did for IPsec. One is the XFR bridge crypto offload, and another one is full IPsec offload. And we also have the Nginx one, and we are doing some work on that. And Paul will talk about that part.
Sure. I'm Paul Pindell. I'm a principal architect at F5, and I've been part of this group, OPI, since the beginning and done a lot of work here. You've seen Nginx Plus running on the DPUs and IPUs. So Balazs showed that. What is that doing? It's acting as a proxy on there, and it's proxying traffic and securing traffic as it comes into the host, and we're offloading those infrastructure functions to the DPU, and then only allowing traffic that the Nginx allows through actually to get to the host where the workloads are running. That's essentially what it's doing. We showed that at a conference at OCP, I think 2 years ago. And we did that on the Marvell card, on the CN106. We did that on the Intel IPU, the E2100, and on the Bluefield 3. I don't wish anybody to have to do what I had to do to make that work 2 years ago. The interesting thing here is that we've got the DPU operator and a OPI compliant set of APIs to abstract some of that difficulty and make it easier for everybody to use. So yeah, Nginx, yes, we sell Nginx, go buy Nginx. I love that, that's great. But that's not the interesting part here for OPI. What's interesting for your OPI is that we made it easier for customers to run the workload of their choice on the cores on these DPUs and IPUs in a standard, easy to use fashion. And so Red Hat had a very big hand in that, coming up with the DPU operator and making it such that, you know, you've got a pod running on the host and a pod running on the DPU or IPU itself. They communicate, and then thanks to the vendors like Marvell and Intel, they've created and done the hard work of creating these vendor-specific plugins. And those are where some of the magic lies. So that's where configuring the P4 rules, using the Marvell SDK, using Doka, those sorts of things you don't have to do anymore to wire up the network paths that you need to make these through the DPU operator. Some of those functions that you want to have happen in the way that you want these cards to be wired up to the host, that's been abstracted through the vendor-specific plugins. So no longer do you have to learn P4 and Toka and the Marvell SDK to make this work on all three cards. You just need to learn the one OPI API standard that is used through the DPU operator. That's the real value add for these demos that you've seen. And the same thing applies to the IPsec portion. There are, we didn't call them vendor-specific plugins, we called them bridges for the IPsec, but each vendor created those bridges for their card so that we could show how to get that very same strong swan functionality running on all of the various DPUs. We're going to see in a later session another workload running on a DPU, and it's going to be, we'll talk about that in a later session here. But for this one, the Nginx Plus is, again, sitting there and acting as a proxy and a security barrier between the outside world and the host. So no traffic that isn't allowed through by Nginx ever gets to the host, and thus we're securing the, in this case, we were running an AI workload on the host. It just so happens that it's Intel OpenVINO. That's the inference server that's running there on that host. And we're protecting that model and that inference server from the outside world with Nginx. But again, the real value add here is that OPI APIs that are implemented through both the DPU operator and the vendor-specific plugins make it easier to deploy and makes it easier to, like Bilal showed, move an instance from one DPU to another without having to understand the underlying, how to wire that up for each of those cards and make it function. And any questions on that and what we did there? Not all. Are you supporting PQC as an offload on the CN106?
I'm not sure. I need to check that one.
Okay.
I'll get back to you.
Yeah. Yeah, yeah. Any other questions? And were there any online? Venkat, did you see any come in online? I didn't see anything flash up on the screen, but.
Can you talk about the telemetry support in there for the network function as OPI as any?
Are there any telemetry functions in there?
Yeah.
Not as part of these demos. We have OTel is supported as an OPI standard, but I'm not sure that that's been plumbed into and created bridges or VSPs for each of the cards. Blas, do you know if that's been done in the hotel stuff?
So regarding metrics and telemetry, we've done a demo at some point where we created our pod that is doing some kind of measurement and exposing that. Since OTel and all these metrics and Prometheus and whatnot and Grafana, you can use those in a standard Kubernetes environment already, right? And since we're extending Kubernetes to the card, we also extend all those capabilities. So even though we didn't particularly try that, a lot of these things turn out to be pretty easy and turn out to just work because we've integrated into existing environments in a standard way. So the answer is no, we didn't try. However, based on what we know from the past, it might be a very small lift.
That would be my guess. Hello? Yes, that'd be my guess. Any other questions? Or was that it?
In the earlier presentation, like pods were shown, like can they be made as AI agents and they communicate with other pods as AI agents to agents communication using Google's A2A protocol?
I think
It's Kubernetes, so I don't see why why you couldn't run those on the card as well. It's just, they're simply pods running. The Nginx is simply a pod running on the DPUs. Yes.
Yeah, so again, it's just pods. And if the card, like from this forum perspective, if the card has, let's say, a chip that can accelerate some of the LLM inference capabilities, and I do believe Marvell's card has that, then that pod can then leverage that hardware. And then, of course, talking A2A is just a part of protocol, right? There's no gating thing happening here. It is open from that perspective, and it's almost orthogonal. So A2A would also be orthogonal, like, yes, of course, but you can also do it on the host. And because the card is just another server in a server, you can do it on the card as well.
Yeah, just to add to that, basically we are looking at accelerating MCP on the DPU. So in that case, that kind of pod would be running on the DPU, and your agents or the server side of the agent would be running as a pods on the host. That's a possibility. We are actually looking at using Nginx Plus for that. Right?
Very good. Going once? Twice? Okay. I think we'll move on to the next one.
Thanks, Vijay, and thanks, Paul. So our next session is from our most recent member of OPI, Fusion Layer. So I would like to invite Ansi to talk about secure ZTP. So they have recently open sourced the secure ZTP code to the community, and they'll be talking about how to use it for the provisioning. Ansi, welcome.
Testing. Hello, everyone. I'm Anssi Söderinen. I'm a senior software developer at Fusion Layer. Greetings from Finland to everyone. And Fusion Layer is a company specialized in IPAM technologies. So like bookkeeping for IP addresses. And also we do DHCP appliances, DNS appliances, and now SFTP. So, can you hear me still? Yep. Okay, so I'm here to talk to you about service deployment using SFTP. So, but first I will tell you a bit about the SFTP in general.
about the challenges and open questions that we still have. Of course, this comes from like a just a developer's perspective, what challenges we have been facing and what questions are still open, how we could do them at all and how we could do them better. And lastly, I will show you an example how we can use SFTP to take onboarding to the next level and deploy a service using it. So before we get to the main course, just briefly go over what the SFTP is. So the idea is that you order a new device, server, or a DPU, IPU, whatever. You ship it to the address where you want to deploy it. And then you have the option to maybe travel there yourself or pre-install it before shipping. But how about you just have somebody press the power button and the device will automatically onboard itself. The device comes up with the correct boot image, applies day zero configuration, and the configuration scripts are run, which handle everything the configuration may be left undone. And with SFTP, that's possible. And it sounds good, right? So although it seems like magic, behind it all is still an SFTP server and an SFTP client. So the easy part is that you can put the server anywhere where the client can connect to. But the challenge number one is to how do we get the SFTP client to the device before actually booting it up, making it actually zero touch. And options are maybe the manufacturer includes the client in the base image, or we use network boot or some platforms auto provisioning tools like Cloud Init. But of course, the future goal would be to have the SFTP client included by default in a standard OS images, for example. Like why should we limit ourselves like to only onboard DPUs, IPUs, even though they are the main goal for the OPI for now? But basically, why couldn't you onboard a normal server also, or maybe even a virtual machine? And we actually have. So briefly, from the server we are serving to the client, we are serving conveyed information, which holds all the important bootstrapping data and owner certificate. It's like your public key to the device users. Your public key the device uses to check that the bootstrapping data was really signed by you and not anyone else. And ownership voucher, like a signed receipt from the manufacturer saying that the device belongs to you. So in conveyed information, you can serve a boot image used for DPUs and appliances, which the device downloads, verifies, and reboots into. Then we have the pre-configuration script. We have the configuration file applied, and the post-configuration script runs. And just to clarify that the configuration file isn't a script, it's like a vendor-specific day zero configuration that the device applies to set up the essentials. So what I like about the SFTP is just not like what I like about the SFTP, it's not just for one vendor or for one operating system. We can use the same standard to onboard servers, DPUs, and other network devices. So just a quick example of a SFTP workflow. So the device boots, the SFTP client starts, and the client collects information on the device, like the serial number that will be used in various authentication tasks. Then we discover the bootstrapping server. The client can read it from a DHCP option, from DNS, or from removable media. And then we connect to the server via RESTconf over HTTPS. And then we fetch the conveyed information, which we talked about in the last slide. And if we are given any redirect information, we will follow it to the bootstrapping server. And then to the main part, we download, verify, and install the boot image and reboot. And then the pre-configuration script runs. We apply the configuration and run the post-configuration script. And we report the progress at each step to the server. So something about the current status of the SFTP client. We have the OPI's SFTP client, but also we at Fusion Layer have tried our hand in developing one. As Fusion Layer has come a member of the OPI, we are happy to look into merging the clients together in the near future. And I would like to highlight a couple of things from this list. So, of course, some of the challenges are like platform specific, like, for example, the DHCP discovery of the SFTP bootstrap server. So rather than reading it from a device's lease file, we tried to actually include a DHCP client in the SFTP client to get like the most real-time data from the DHCP reply, and therefore discover the actual bootstrapping server. And here we actually run into like an issue like that this only works for Linux, for example. So you might have to wait before we get to onboarding your Mac servers. But yeah, this is like just an example of many when we try to make the client universal, but we are now, of course, focusing on the most used operating system and architectures. Also, one of the major questions here is that what do we do about the boot image? Like about the boot image, now it mostly concerns like DPUs, IPUs at this stage, but in the future, maybe some other devices as well. But I don't think there is any like universal way of doing this. Like the OPI lab repo, for example, has a section about updating the firmware, but it's just marked as a to-do for later. But like I'm just thinking this from an SFTP client developer's perspective, that we actually need some universal way to tell the client to update the boot image, like verify it and reboot the system. And I think the same goes for the applying the configuration file. The device can handle it, I guess, in its own way, but we are still missing some universal command to actually apply it. And now to the fun part, actually. The standard, actually, the RFC standard doesn't mandate the script language. And we have been using SH and Bash because they are near universal on Unix-like systems. But however, the language could be anything that the device and the client support. So here we are finally dipping into our topic today. And instead of like using the SFTP to set up initial user, maybe SSH keys or something like that, and networking, why stop there, as we can like set up the services from start to finish with SFTP. So here we can see a really simple setup that can be run via SFTP, but of course you can write as complex as you want. Okay, so I have a small demo for you about the onboarding a service using the SFTP. I wasn't too sure about the connection from here to the lab, so I took a liberty to film the demo beforehand. So any SFTP server will do as long as it follows the SFTP RFC. The screenshot you are looking at is part of Fusion Layer's own proprietary SFTP server solution, but which I'm using for this demonstration to show you what an SFTP server UI could look like, and maybe even change the way you look at SFTP as what it can do. The idea here is that using the UI, we can add a new device, we can pick a service from the catalog, it will create a pre and post configuration scripts, which we can still modify before activating the device, thus allowing the SFTP client to connect to the server. So it's a small video, but so here we are selecting the service that we want to set up while onboarding the device with SFTP. The device in question is a server running Ubuntu. And here our server automatically generates the necessary default configuration scripts for installing the service. I'll press play. Okay, so the scripts are actually written as Bash. The required commands here are quite simple to actually onboard it. So using the package manager app to upgrade the system packages and then install Nginx. But you can build more complex scripts when needed. And we can modify the scripts even before activating the device. And I just deleted some unnecessary lines that we don't need here. So as I'm now activating the device, the SFTP server sets the device ready for connections, and the UI displays that we are waiting for the client to connect. And next up, I will start the SFTP client on the target device to start the discovery and the connection. And already we can see the SFTP server receiving reports from the client. We are waiting for it to upgrade the system packages and then installing the Nginx. And now, as the client reported the configuration script output back to us, we can view it from our logs. I know the text is small, but it shows the package manager output, and lastly, the service status for Nginx. And so this all comes from the client. And now let's verify that the service actually installed and is up and running. Just a moment. It seems to be up and running. And now let's check that the device IP address and verify that the Nginx actually answers. Yeah, and it seems to be successfully onboarded as we wanted. Yeah. So just a quick note that usually onboarding is referring to the day 0 configuration, while the day 1 configuration is usually done by other orchestration tools or even manually. While using the SFTP for day 1 configuration straight away to set up services is handy. The configuration script need to be tested before they are deployed. We could, for example, spin up a virtual machine with the similar specs and OS to run the configuration script to verify that the services are up as planned for activating the target device in the SFTP server. So overall, we will still have work to do with the SFTP, but the solutions and flexibility it offers already at this point cannot be denied. I personally see that the SFTP does have an important role to play in the future. So thank you.
There we go. A couple questions. I know that that we can use SZTP to get the initial IP address on the card so we can address it and all that good stuff. But we need the SZTP client on all of the cards. Do you know which ones already have that client baked in? Which cards have that baked in? I know OPI, one of the things that OPI I think was successful in was convincing the vendors to get a Redfish client installed on all the cards. And I know we've talked about getting SZTP client installed on all the cards. Do you know which ones have done that already?
Sorry, I can't really remember. I think, well, at least in the like pre-baked, I don't think any of those have.
Okay. Vijay, do you know if is the SZTP client on the Marvell CN106? Is that baked into the base firmware? The SZTP client? Yeah, I can't. So I know I've done demos where we've shown each of the cards once it had a client on there doing all this work. I just don't remember which cards have the client on there and which ones don't. Swati, do you know? On the IPU? It's there, but don't use it. Okay. So it sounds like that's an area we need to work on, is getting the vendors to work with you all to get a workflow figured out there, like especially that ownership certificate work. What do you call ownership? Voucher.
Yeah.
Get that voucher on there, and in a standard way. I'm excited for what you guys are doing here because it is a difficult thing. Like you said, you ship a card and then you call the lab manager to go figure out what the IP address is once it comes up in DHCP and you go through this. It's a manual process, and that's the goal of SZTP, is to not make it manual, and I like that. But
yeah, especially like for example, when talking about non-DPU, for example, so we still have the question about the SZTP uses certificates to verify and secure the connection. Like if we want to onboard some other device than DPU, how do we get the search there? Do we need to do that manually, or is there a better way? But yeah, but one of the major questions here is that the boot image, how do we do that, like universally on all DPUs and devices? Thank you.
I had a question.
Sure.
Is your software open, or?
The client, SZTP client is open, and it's under Apache license. But the SZTP server, it's a proprietary product of FeatureLayer. Yeah, exactly. Yeah, so sorry. Exactly. The SZTP server is not on the card, so only the client. And it doesn't really matter like which SZTP server you're running, as long as it's like the RFC compliant. Yeah. Thank you.
Thanks a lot. Thanks a lot, Ansi. Is there? So there is a comment that says, just a second, let me check. Oh, the initial portion of this ZTP approach looks similar to FIDO specification for device on board NIS TIR 8259D. Have you looked into it?
Well, sounds familiar, but mostly I have just looked into the SZTP RFC and not FIDO, but I will check it out for sure.
Thanks. Okay. Thank you. Thanks a lot, Ansi. So the next, we have a panel session. I would like to invite the panelists to come forward. And first, we have Jyotsna Chitri, who is also our governing board member and OEM partner manager at ARM. Jyotsna. And next we have Yahoo Galon from Excite Labs. He's the VP of the DPU software at Excite. Then you have Balaz Namet from Red Hat. So I would like to say, you would have seen the schedule. The initially scheduled participants couldn't join in the last minute, and I really thank Balaz for volunteering and joining this session. Really appreciate your support for the project. I think both the Deloittes and JP Morgans couldn't join. I don't know. Thanks a lot. Over to you, Jyotsna. We don't have any slides to share, so all those online participants, you just have to listen. Yeah.
Hi, everyone. Nice to meet you all. I'm Jyotsna Chitri. I'm from the infrastructure line of business at ARM. I actually lead the networking and edge segments. ARM has been part of OPA board member, I think, for a few years with the goal of enabling the wide adoption of DPUs, seamless integration of all the DPUs, how they operate. Most of them are ARM-based today. I think OPA is doing a great... can you hear me okay? Okay. I think we're really grateful for OPI for all the work they're doing in that path. I think the topic for today is we've seen how DPUs are helping in a traditional data center environment, but what's their role as we move forward to an AI infrastructure? So I think I'll start with a couple of questions, high level, maybe in that aspects. So what's typically the challenges that you're solving today with DPUs in data center, and how you see they help or they're critical for in an AI infrastructure, for example, to offload in an acceleration path, to enable of the AI to, GPU acceleration path, things like that. So any thoughts how you're thinking of leveraging DPUs in that context?
Yes. Can you hear me? Okay. Hi, everybody. First of all, I'm speaking on behalf of DPU vendor. We are Excite Labs, and we came up quite recently with a product. If you want to know more, we have a couple of our guys at the table back there, so please do reach out. I think, first of all, there are a lot of similarities in AI infrastructure for DPU, front-end network facing offloads as to other use cases that are out there. You still need to take care of dealing with multi-tenancy and data acceleration, storage disaggregation. So all in all, there are a few specifics, but we are seeing those things as quite being similar. By the way, on top of that, DPUs, the way we see and feel the market, not always or not just have to do with being server attached. And we see a lot of ways that DPUs are being consumed, whether as appliances or smart switches. And I think similar things apply, including what you need to do to get the lifecycle management and provisioning of those devices.
Thank you. You have anything to add?
Yeah. So one of the biggest challenges that we've seen is that each DPU tries to be a snowflake, right? Like initially, it's more like, oh, but if you talk to a vendor, it's like this DPU is not exactly like the rest, and it's different. But if you zoom out, they are more similar than they are different. So you need to treat them in the same way. So a lot of the work that we've been doing is really pushing towards this. Let's have a server inside a server. And once you get to that picture, it's the same story. Like if you're solving AI issues on the host or on the card, it should also all be the same, right? And yeah, so the main point on that is since AI as a technology is moving so fast, you want something that's super flexible because you don't know what's going to happen tomorrow. So as long as it's a general purpose platform managed in a unified way, then you can cater to those changes in the industry.
Thank you. I think that brings to other question in terms of workloads, especially how do you see the split between the DPU and host today, or the context of AI, the distribution, what's typically can be offloaded?
Yeah. So it really depends on the capabilities of the DPUs. In the end, you want the user to have the capability to move it down, even though it might be slower, right? So some DPUs have embedded hardware devices, and you have to talk to the vendors to understand better what kind of parts of that AI workload can be accelerated, right? The interesting piece there is that the DPU sits in front of the host, so all the networking goes through the DPU before it hits the host. So if you can cache, or you can look at use cases like LLMs, like VLLM specifically, and figure out how you can use the memory on the card before you burden the host, or like offload some of that. That's where I think the most gains would be with the DPUs, in addition to those accelerators that are very specific. Like there's specific inference accelerators that could make some of the use cases better. So again, the idea is you can run anything everywhere. Some things run better on the host and some things run better on the card. And it depends on those like hardware details.
Yeah, I'll try to add to that. So specifically, if we look at the inference workload, a lot of load balancing can be done directly on DPUs. So basically, if you're facing the front-end network and the storage, you would like to get more direct access to GPUs rather than going through host systems. That makes a better utilization of the overall system. You will save some PCIe bandwidth and so on and so forth. So that's one use case. There is a lot of pre-processing also in the training workload that can be done, batching and doing those pre-processing steps. And once again, it makes a lot of sense to do that on DPUs that have at many times a lot of flexibilities and accelerations in between the network and storage and the GPUs.
Yeah.
I think that brings another question in terms of security. If you're bypassing the host, what kind of enhancements or things we would require on GPU so they're autonomous in terms of data management and doing that with the other GPUs and stuff independently of the host?
Okay, so one perspective is that the DPU is part of the infrastructure, right? Like it's managed by a separate administrator. So it's about responsibilities. Do you give that responsibility to the administrator that manages the host or the card, and then ensuring that there is a security boundary between the host and the DPU? That's the main perspective here.
Yeah, I tend to agree. I think that we see different deployment models for AI. In some of those cases, you might care less about that level of isolation if you're running a very large LLM model inside, one of those big guys that are running those, and everything is fully bare metal level allocated to this workload. That might matter less, but then again, maybe more about inferencing or other smaller things, then I think it comes once again to the multi-tenancy requirements and your ability to provide that air gap between DPUs and the host system, in which case, I think what you said definitely applies.
Yeah, what I would like to add here is if you take the perspective of you are giving root on the host as accessibility to anybody, the DPU should just survive anything that gets thrown at it, right? So maybe it is running some kind of deep packet inspection with some kind of AI embedded inside that pipeline on the card. The host should not be able to interfere with that. Like it's literally that. You give a root to the host and it should survive anything that you throw at it.
The other thing I had a question for you on is on your status for the DPU operator. I think maybe if you could give some overview where you are today, I think that'd be helpful.
All right. So actually, we had a talk quite recently, but honestly, we are quite early in the process. We as a DPU ASIC vendor, we are an ASIC company. We have sampled our device earlier that year. All in all, we believe that it will come very native to us. We are like heavily supportive of open source in general. And I know you have some hard requirements on that side, and we believe we can fulfill that. But so the short answer, we are not there yet, but we have looked at it and we see the value definitely around lifecycle management. I do want to refer to one point you said earlier in your talk, which was about making sure you can offload first, accelerate later. So I tend to agree. Then again, customer wants to see the value upfront. So you want to offload and see that it accelerates. Otherwise, it's hard to say, what's the ROI and get a more pull from customers. So, I mean, we spent a lot of energy and time into the design, the architecture, and the software to make sure that once you offload, you already see the value of acceleration. So our focus is honestly a lot around that right now, and I think rest will follow, including DPU operator support.
Thank you. I think I'm going to another most fundamental question on how DPUs really are fitting into an open ecosystem. What are the typical barriers you're seeing for multi-vendor support? I think that's still the case. I think we haven't solved it 100%. But maybe if you can throw some light on what are still the barriers for that multi-vendor support.
Yeah. So from my perspective, if a vendor has any proprietary components, so this is the biggest red flag. Like they're bringing some SDKs or something that I need to go behind a paywall to access. That's a barrier. That's a huge barrier. Anything like, even the documentation that is not open, that is also a huge barrier. So from my perspective, if the vendors are making it more difficult because they're afraid that they're hiding some kind of IP behind some paywall, I think that's actually going to backfire. You need, for especially OPI, you need a full open environment, and everybody should be confident about making it easy to use. And of course, there are some particular aspects of certain DPUs that are better than others, and let that be the case, but let that be the case behind the scenes, not so much in a way that affects the usability.
Yeah, I don't have much to add, rather than, I agree. We also truly believe that everything needs to be open sourced. We are sharing everything, everything, including everything at the source code level, including data path stuff with our customers. We will open up all of that to the rest of the world, and I believe that will help adjusting to our device. And in general, I think standardization and openness is key to getting to that desired goal. Yeah.
So what I would like to add, especially since I'm speaking on behalf of Red Hat here, is that there is a difference between source available and truly open source, right? So if you are making the source available, but you're limiting what can be done with that to a weight, like a ridiculous level, then it's as good as it being closed source. So that's also important.
We hear that a lot of complaints from the end customers in the sense like it's not truly open. It's also still vendor specific, tightly coupled. I think other panelists were not here, but one thing I was curious is how much is the push from end customers that enable these vendors to actually do that? Because I think even from our side, we keep going to our vendors to support it. It's not always, I think, not the case unless some end customer pushes for it. Do you see that being an important thing to make that more open source, maybe?
Yeah, so what does open source really give you? It gives you the ability to dig in and figure out the issues, right? Like that's, in a nutshell, what it gives you. And from a Red Hat perspective, if a customer has an environment and it's working, then nobody will care that it's open source or not. The problems arise when something goes wrong. Right? Like on a weekend, something goes wrong, and you can imagine that an engineer has to go in and figure this out, and then that person then hits a binary blob, and he can only look at the assembly to try to figure out what's going on, and that won't work because it will not be productive. So in the end, it will hit your bottom line because that problem will have material effect on how fast you can fix these things. And this is where I think open source is absolutely necessary for these kinds of problems.
Yeah, nothing much to add. Point taken.
Okay, I think the final question, probably I want to leave it to the community here is like, what do you see, like how OPI can help to solve the challenges for future, again, especially maybe in the context of not just the infrastructure, but even still, we, I think, struggling with what we have, the challenges with data center. Do you see any other requests for OPI that we can enable or contribute?
So the biggest ask is to get customers engaged, right? So as everybody knows here, it's been a chicken egg issue since the beginning. We don't know what customers want. Customers don't know what they want. So we need to build the MVP and we need to get that feedback. So any point where you have the chance to talk to customers and say, are you interested or something? Use that and get it into their hands. Like give them the SSH access, give them all the documentation and really ask them like, what is it that you're still missing here? Even if they tell us that what we have is not the right thing, that is valuable as well. Without the customers, there is no need for any OPI, right?
So customer feedback, yes. I agree.
Yeah, I mean, at the end of the day, customer is king, and we need the pull from customer. And some customer may care less about certain things. Some customer may care more. Some customer may want to keep their stuff closed. Some customer won't. So there definitely needs to be a lot of pull from customers and network and storage function providers.
Yeah, and I truly believe the amount of work that has already gone into OPI is enough for customers to take the next step.
Okay, thank you. I think it's really helpful. Thank you for your insights.
That's a good observation, right? That we have enough, right? So if we have enough, how do we drive the adoption to the next level? We all know we keep saying, chicken and egg, but how do we drive the next step? There is not enough information out there, or when you are talking to, again, the question is also open to everyone, right? That when you talk to your customers, what are you hearing as their do you see that, hey, if you do this, I will jump in and do that, and things like that? Maybe, share your thoughts. And also, question is open to others here.
So from my perspective, the first thing is you need to talk to the person who has decision power, right? Like it's a lot of the cases you start talking to somebody who will have influence on the person who decides, but it won't be the person. So you need to figure out who is really taking the decisions here. And then it's about showing that an existing environment can be extended rather than rebuilding something from scratch, right? So everything that we've done here is really taking the cloud native perspective, extending that infrastructure to the DPU. So there is actually no real reason why you would not just take your existing deployment and move some of that to the DPU, right? This is what we can do today. So that really lowers that entry. In the past, it was more like, okay, what do we need to change to make it work for you? And now it's more like, okay, you take your existing solution, let's just tweak it a little bit, and let's just start using the DPU in whatever way it makes sense to some degree, and then we build from there. That's like step one. And really think about what's the next smallest thing that you can do to move this forward. It has been the case since the beginning of OPI that we wanted to do too much. Like we wanted to boil this ocean. It doesn't work. We really need to just take that small step. As long as we're moving forward, I think we can get somewhere.
So Balaj, I think you had a good point about being able to modify existing environments, right? So do we have these upgrade paths and method of procedures documented for OPI?
Documented, we don't. That's always the difficult part. There are some blogs that talk about specifically this idea that DPUs should be enabled in a cloud-native fashion, right? If there is somebody who is a little bit technical, right? You don't need a lot here. You just need to understand cloud infrastructure in general, and then add to that knowledge by doing just a little bit extra, and that will show you how this can like seamlessly extend. Since you're treating DPUs just like any other node, if you have an existing environment and you're scaling horizontally by adding another node, the idea is the same. You're now scaling also horizontally, although the DPU is below. It's still kind of a horizontal scaling. So that's the idea here. Just another node and extend by moving it down.
So I have a question on the role of IPUs and DPUs in the backend AI infrastructure versus the front-end AI infrastructure. And I think you did talk about some of the use cases, but I would like to really see what are the thoughts in general in this room about having DPUs and IPUs play in the backend GPU interconnect infrastructure.
I can try. First of all, the way we look at that, the boundaries between what makes a DPU versus what's nowadays called AI NIC are slightly vague. And we know different approach to dealing with that. We believe that in backend network, definitely in the scale out, there is a play for DPUs because of the programmability, whether it comes to transport level programmability, congestion management, customizations, as well as doing some pre-processing in between GPUs in a multi-GPU cluster. So I think on those backend networks, definitely we see a lot of traction. I think it's currently a little bit outside of the OPI scope, but and I'm not sure how that could fit into there. But as a DPU, definitely we see very much a lot of relevance, also on the storage side.
Okay, yeah, I think that was the main question, and then the follow-up was like, OPI standardization for those backend things. What can be addressed and done here? That will be a good discussion topic, I think.
Want to try?
I'm gonna try. So if you think about a backend where like everything happens behind the scenes, right? Like the DPUs are talking to each other. Maybe there's some GPUs that are talking to DPUs, and there's maybe GPUs inside DPUs, and everything is a composable compute entity. Everything becomes a node. There are a bunch of APIs there, right? From my perspective, it's not necessarily a DPU specific problem that you need to solve, right? So if you look at the industry and they are being solved at the x86 level, the host server level, we have to apply that and we have to follow that industry. You don't want to reinvent the wheel. AI is going to move forward without DPUs, and we should just follow along and do the same thing on the DPUs.
Hello. Yeah, so I think for a AI backend NIC, for training, maybe OPI may be less relevant because usually people don't deploy things on scale, everything runs on bare metal. And the applications which you have would be usually RDMA, protocol offload, and your security would be MACsec at link level security. So, but for inferencing, I think it makes a lot of sense because inferencing can be deployed in a public cloud environment also. So where you can offload certain things to a DPU there, right? So. Yeah.
So that's a good point, right? Inferencing is a bigger market,
Right.
growing than definitely faster than the training side of things, right? One idea, Vipin, could be aligned with SNIA, storage.ai. They just started. They're looking at how do you do ingestion, how do we do checkpointing. There are issues in terms of how storage interacts with the security side of things, how storage interacts with the network, compute, all that, right? So. Maybe aligning with them to kind of understand what the challenges are and see how that could get mapped to what we do here could be one suggestion. Yeah.
See, especially like Can't the DPUs handle the MOE routing of the traffic to a specific uh, expert? Like I think like MOE architectures are becoming very popular now, like in the training models as well as inferencing, like they are moving away from dense architecture to MOE. So there is a routing functionality. Instead of routing functionality running in AI factory, why can't that be offloaded to DPU? That's one. And the data processing, why can't we do data for parallelism work, where like when the data is fed for training models, that initially comes to DPU and it takes care of distributing the traffic to the respective GPU nodes.
Yeah, yes, I do want to try, right? So, but we may have to define the problem maybe one more level of detail, because it might be just the traditional networking and routing load balancing. If that's what it is, we should go back to the bare minimum we are talking about, right? This is DPU is part of the infrastructure. It is part of the distributed infrastructure. Then, if the problem is just going back to the traditional, which I believe it is, right? I'm not saying that we don't need to focus, but I think if we focus on AI, anything AI, it's easier to talk to customers and budgets and whatnot, right? So in that sense, yes, that's useful. But in terms of is it something else that we need to do is not quite clear. To me, it sounds like a traditional.
Yeah, especially like with respect to the MOE architecture,
Yeah.
I think like initially, like as soon as the request comes, the prompt request, the prompt needs to be sent to the right expert. I think like instead of giving it to uh, the regular like CPU processing to find like the right expert, like I think if that can be offloaded to DPU, so there is no need for CPU to get involved.
So what you're describing is like in the mixture of experts model, there's only like literally one piece of that model that gets activated. And if you look at it from like a TensorFlow perspective, it gets deviated to that direction. So what you need is an AI router, right? And again, from my perspective, and I think Venkat is saying the same thing, it is not so different. Like it's an AI router and you can slap on that label and everybody will be very happy. From a networking perspective, it is just like a router. And definitely we need to offload routers. I completely agree with that. If it's a layer 3 router or an AI router, it is a router. And I do think those things can move down. And then it's a matter of, okay, is the DPU capable enough? Do we have enough resources? Or does the next gen DPU have enough? Because a lot of these problems, you get myopic by thinking, oh, my DPU is just an ARM server and it's not that powerful. And that's wrong. Because if you take that stance, then you will limit the architecture to the hardware. And you need to build this in a way where it's general purpose. And yes, you need an AI router, could be running on a host, could be running on a card. And maybe not today, but maybe tomorrow. From an architecture perspective, you need to have the capability to allow it to run there.
Okay, thanks a lot. There are no further questions and comments. Then we will take a break now. Thanks a lot to Jyotsna, Balazs, and Yao. Really appreciate your comments. So, to online attendees, we will take a 30 minutes break. I know we are running 15 minutes late, but for the second half, one of the speakers cannot make it. So for the lightning session, so we are good with the time. We will definitely end at the right time for lunch. So let's take a break and reassemble at 11:15 then. Hi. Okay. We'll begin our second session. I hope everybody can. Yeah. Our second session is we'll start with talking about the interconnects in the AI infra with DPUs and IPUs. So we have Pani, who is the executive director at the Synopsys, and also principal engineer Rajesh at the Synopsys. So the Synopsys team will be talking about the interconnects. I welcome both Pani and Rajesh. Thank you.
Hello, everyone. Hello, everyone. Welcome to the presentation on interconnects for AI infra and AI infra for DPU and IPUs. I'm Fani Suresh Paladagu, a product management professional at Synopsys, and my colleague Rajesh is principal engineer at Synopsys. Synopsys is a leader in EDA and semiconductor IPs that can enable our customers for like a silicon to system solutions. Yeah, silicon to system solutions. Today we'll be talking about AI revolution, bottlenecks, interfaces for high performance computing and data centers. Key interfaces like PCIe, CXL, Ultra Accelerator Link, and Ultra Ethernet. Rajesh will be covering high-speed interface implementation aspects as well as the challenges for PCIe, CXL, UA-Link, and UC. We'll wrap up the session with next-gen interface needed for AI infra, followed by Q&A. So most of the friends and colleagues, like they were talking about like the application level aspects and like more of use cases and things like that. What we are going to cover here is things that happen behind the scenes, like the interfaces that are key for like DPUs, IPUs, GPUs, and accelerators. These are the key interfaces and the protocols like that we'll be using based on the specific use case. So as we are aware, like AI is creating a lot of need for like compute demands and things like that, and model sizes are doubling every 3 to 6 months. So that puts like a multifaceted design challenges. So we have to look at like optimizing the performance, power, area, and the latency for most of these applications. So the increased compute demands puts a lot of pressure on interface and the memory technologies to deliver high bandwidth as well as with a low power and latency. So if you look at the current technologies, 1 petaflop of compute needs like a 3 to 4 terabytes of HBM and up to 1 terabyte of PCI and Ethernet. Like the right side, so with these increased compute demands, like memory standards as well as the interface standards are under a lot of pressure. They need to evolve. And if you look at the graphs, like they are like increasing exponentially. In the past, like each of these standards used to take like a lifetime of like 3 to 4 years. But in the with the current trend and how the AI is evolving, so we have to like, there is a churn of like each standard in like 18 to 24 months. In order to meet the requirements, like the data rates are increasing exponentially. So if you look at the high performance computing domain, like there are 6 primary functions in the SoCs, like accelerators, CPUs, NIC, switches, storage, and retimers. All these 6 primary functions needs bundle of like different interface IPs. If you look at the right side table, like based on the specific functionality, like we need a bunch of interfaces. Like let's start with the accelerator. It needs PCIe interface, Ethernet, Ultra Accelerator Link, memory interfaces. And if you're dealing with the chiplets, then obviously you need die-to-die as well. Look at the NIC requirements, like it needs PCIe, Ethernet, die-to-die, and memory interfaces. So these are the key interfaces that are needed, like most of these application the functions. So let me get into the details of the PCIe interface for high performance connectivity. So PCIe is a high-speed interface that will help to data transfer between the NICs to CPUs, CPUs to the accelerators, and CPUs to the SSDs. PCIe is used in like switches as well as the retimers, and it has a wide variety of applications. It can be used in automotive, IoT, as well as aerospace and defense applications as well. So this particular interface is highly configurable and a scalable interface. For example, based on the bandwidth requirements, each macro can support 1 to 16 lanes of PCIe. So if it is meeting, like 4 lanes is meeting our requirements, we can use 4 lanes, or like if you need 16 lanes, we can go for 16 lanes. And if 16 lane bandwidth is not sufficient, and if it is demanding like a more bandwidth in order to meet the overall throughput requirements, we can instantiate multiple 16 lane configurations into the SoC that can get us like the bandwidth that we are looking for. And the PCIe standard is like a backward compatible. That means currently we are at like PCIe Gen 7 running at 128 gigabits per second. So once we design the SoC for PCIe Gen 7, it has to be backward compatible. It should support PCIe 6 and up to like Gen 1, which is at 2.5 gigabits per second. And PCIe supports like low power states as well. So that helps us, for example, if you're not using the link, we can just power down it and like save the power during the idle states. So moving to the CXL, revolutionizing the data center architecture with the CXL. CXL is a Compute Express Link standard that is built on PCIe infrastructure. So it leverages the high-speed path of the PCIe, and it also supports like a few additional protocols in addition to the I/O path. I'll get into the details. So CXL mainly addresses the memory bandwidth bottlenecks in the servers, and it is like designed for optimizing the latency, and like that gets us like low latency when compared to the other protocols available out in the market. So it has 3 different protocols, like a CXL.IO. As I mentioned earlier, it is like alternative to the PCIe. It leverages the high-speed IO available. And CXL.Cache. This particular protocol enables the high bandwidth cache coherent access to the memory for accelerators as well as the CPUs. And the CXL.Mem protocol enables the low latency access to the memory for the attached CXL devices. So there are like 3 types of the CXL applications, like a type 1, type 2, and type 3. Type 1 is like accelerators without memory. We can take NIC as an example here that leverages the .IO as well as .cache protocol. And the type 2 devices are the accelerators with memory. You can consider as like a DPUs and GPUs are as example. And it leverages all 3 protocols available out with the CXL. The third one is a type 3 device where like we'll be using .IO as well as the .mem application. This is mainly for the memory buffers as well as memory expanders and the pooling devices, mainly to address the memory challenges. So most of you have heard about the scale up and scale out. So Ultra Accelerator Link is used for the scale up applications as well as Ultra Ethernet is used for the scale out applications. So as the model sizes and the parameters are increasing, so it is very difficult to store all the models within the single GPU or DPU memory. So in that case, like we have to share the memory across the DPUs or the GPUs. And these are the protocols that will enable us to share the models and synchronize between like different GPUs so that multiple GPUs can act as a single giant GPU that can perform the entire task. So Ultra Accelerator Link will enable us the scale up, that is like vertical scaling, and Ultra Ethernet will enable us the scale out, which is like a horizontal scaling. If you look at the diagram here, the one highlighted in the blue is like the vertical scaling that uses the Ultra Accelerator Link, and the one that shows like between the clusters, that is Ultra Ethernet Link that helps us with the scale out options. So for the ultra accelerator link, there are two different variants are available out in the market. UA Link 200 that leverages the 224 gig Ethernet physical layer as a baseline, and like the protocol is built on top of it. This will get us the highest bandwidth available out in the market as of today, and that is mainly used for like AI training purposes. And there is another variant, UA Link 128. So this leverages PCIe Gen 7 physical layer infrastructure. So, and this is mainly suitable for AI inferencing applications. So the ultra accelerator link will enable us the direct load, store, and atomic operations between the accelerators. That will save like a lot of time and minimizes the latency, overall latency contributed by the protocol. The Ultra Ethernet will enable us mainly to address the AI and high performance computing scale out requirements. This is also like a very high speed protocol that leverages 224 gig speeds, and it is also configurable. We can configure from 1 to 8 lanes, and we can have like a multiple 8-lane macros within the SoC to get to the bandwidths that we are looking for. And this particular protocol implements intelligent congestion control for managing the intense burst traffic. This will help us to address the congestion when we are communicating across the GPUs and the DPUs. This is mainly focused on the AI workload, resource sharing and synchronization among like up to like 1 million endpoints. So if you look at the bottom right diagram, like that gives us like we can have a crossbar connection between different GPUs within the pods and across the clusters. Okay, so I will hand it over to my colleague Rajesh. He will be covering high-speed interface implementation aspects as well as the challenges associated with most of these protocols. And
Thank you.
So, where you said now, when do you think we'll see availability of hardware that actually supports UA Link and Ultra Ethernet? Well, that's question one. And question two is Ethernet for scale-up networks versus UA Link for scale-up networks. And you just saw the OCP, another set of announcements around scale-up. Everyone seems to be going dog for scale-up these days. Kind of interesting. And so really, the contrast between the UA Link approach and the Ethernet approach, how does that play into what you're saying?
Okay, yeah. As of now, like I mean, as I mentioned earlier, we are an IP company. We are enabling a lot of customers with the UA Link as well as the Ultra Ethernet as of today. And there are like a lot of vendors and customers out in the market. They are working on these specific, leveraging these protocols. They are designing their SoCs. So there are some customers already rolled out their products with the UA Link and Ultra Ethernet at 224. Most of these things are like very early stages. So as I mentioned earlier, like Ultra Accelerator Link is mainly for the scale-up applications that can go up to like a few hundreds of interconnecting the GPUs and the DPUs. But if you look at the Ultra Ethernet, that can get us like to up to like 1 million endpoints can be interconnected. So that is at a larger scale, and the UA Link is mainly designed for like with a limited set of few hundreds of the GPU interconnections. So within the pod, we can use, for example, if you look at this diagram, within the pod, we can use UA Link for interconnections. Yeah. Yeah. Really good question. I was expecting this like because it was announced like 2 days back, right? So if you look at the scale-up aspect, right, there are 3 different ecosystems available out in the market as of today. Most of us are aware of like NVIDIA NVLink. So they are using their proprietary ecosystem, And Broadcom, sometime back, they announced Broadcom SUE, scale-up Ethernet, because Broadcom is they're experts in like Ethernet. So they decided why to use like a different protocol. Let me repurpose the existing Ethernet and leverage for the scale-up, right? So they announced like a scale-up Ethernet sometime back, and Broadcom, they have their own ecosystem with Tomahawk switches to enable the scale-up using the Ethernet. And the third one, open standard, is the ultra accelerator link. So a lot of market leaders out in the market, they are working on the ultra accelerator link, but the ecosystem is not fully ready yet. But this is an open ecosystem. So once it is ready, I think this can enable like more openness with respect to like NVIDIA and the Broadcom. So Broadcom, they already have the scale-up Ethernet. They collaborated with the OCP. I think that's the reason like they announced like eSun. So I think they are going to leverage the existing Broadcom scale-up Ethernet and like make it like more open and enable to like a lot of other vendors as well. That's my understanding. Yeah, thank you.
And I guess how all this has something to do with DPUs and standard interface via API.
Yes. He's going to touch on the implementation aspects.
I always want to jump to the final thing. Because
hello, everyone. So I'm Rajesh. So my expertise is in subsystem implementation and interconnect technology like PCIe, CXL, Ultra Ethernet, and UA-Link. So I do designing and I have exact idea in how it's going to fit into SOC. So my presentation is, my first slide is about the PCI interconnect subsystem. Here highlighted in the purple, I have highlighted like PCI subsystem and with the basic building blocks, but the strategy is same for either Ultra Ethernet or UA-Link. That you will have a controller PHY and you'll have a clocking reset structure, control logic and custom logic. So overall, the implementation strategy will be same. So talking about subsystems, right? Like here, if you see, we have highlighted in the purple, the first building block is a controller. Controller generally acts like a brain of a subsystem. This is a protocol specific based on the application. It can be programmed and that it connects to the application logic, which is sitting in the SOC through AMBA bus. AMBA starts for Advanced Microcontroller Bus Architecture, and this is provided by ARM for SOC on-chip communication. And then the next layer is kind of a PCS, is called physical coding substrate. This is a layer which is sandwiched between the controller and the PHY. What it does is it encodes and decodes the data which is coming from the controller side and make sure that it's more reliable and understood by the PHY. Coming to the PHY, so within the PHY, we again have two sublayers. We call it PMD and PMA. So PMD stands for physical medium dependent. It is a glue logic. Along with that, we have a PMA, which is hard macro. So PMA stands for physical medium attachment. So overall, the combination of PHY would be like a PMD plus PMA. The main functionality of it's any digital logic which is coming from PCS is converted into electrical signals, and then it's being transmitted to serial link through PCI link partner. And the data uses a serial bus architecture that uses a lane, utilizes lane for the data transfer. So data which gets transfers are in like a packets, and it has some additional bits being added for encryption and error correction. And this gets connected to the link partner through serial bus. So here, if you see in the diagram, I have like X1 link and X2 link, just to show you that when I say X1 link, it has a single lane. When I say single lane, which has TX and RX, highlighted in the orange is TX, the one which is in the blue is an RX. So when we say X2 link, we have two lanes in it. The next slide is about PCIe. I think my friend already covered it, but PCIe stands for peripheral component interconnect. It's a standard component in the computer which is used to connect either network, GPU, or SSD cards. And in this slide, what I want to show is like we have a series of PCIe generation spec releases. If you see, I would like to cover mostly on PCIe 6 and 7. If you see PCIe 6, it has a data transfer rate of 64 gigatransfer per second. And when I'm talking about a single lane, it is 8 gigabytes per second. And then for X16 slot, it would be 128 gigatransfer per second. Now, the PCIe 6 was released in 2022, and then in the recently, like PCIe 7 spec was released in 2025. Here here the data transfer rate is 128. It's almost double the data transfer rate of PCIe 6. And comparing to X16 slot, if you see, it is 256 gigabytes per second. So it's a massive increase in the bandwidth. So I would say like for every generation of PCIe release, the bandwidth is kind of doubling for every generation. Here, what I want to highlight is like, PCIe architecture is a backward compatibility, and also it can support bifurcation and aggregation of the logic. In my next slide, I would cover about what do I mean by bifurcation and aggregation. And here, if you take an X16 link, it can be connected into two S8 like four PHYs, or it may be connected into multiple combination of 4 PHYs. Coming to the CXL, it's a Compute Express link. It's a totally new protocol which gets added on the top of PCIe. So in the implementation background, the CXL is an additional set of logic which gets added, like apart from the PCIe logic which sits in the controller, it has an additional logic which gets added into the PCIe. And generally, this logic operating frequency is double the frequency of the data operation. So it's fairly critical when we have a PCIe with CXL protocol. The timing closure becomes very crucial in the design. And I would like to touch upon CXL.io. So it has mainly three sub-protocols within it. When talking about CXL.io, it ensures and manages that communicate like a PCI device. And the next is a CXL.cache. It provides a cache coherence to the memory access. So what does it mean is, like if you see in the diagram on the bottom, like accelerator can you have a CPU and accelerator, and it is connected through PCIe and CXL bus. So accelerator can access the CPU and cache its memory. Similarly, CPU can access the accelerator and cache its memory. So that the memory between the CPU and accelerator is kind of consistent, and any change in the memory is known to each other. Coming to the CXL.memory, so here, like any device which gets connected through CXL.memory protocol, it exposes its memory to the host CPU. These are the basic three protocols of the CXL logic. Okay, so this is an important slide because I want to highlight that if you see in the picture, we have a CPUs, we have switches, we have a NIC, a DPU, and GPUs. If you see here, like a PCI is everywhere. PCI is getting connected between CPU to CPU. It is getting connected between a NIC to PCI switch, DPU to PCI switch. So in this picture, it is PCIe 6, but it can be PCIe 5, PCIe 6, or PCIe 7. And in my next slide, I would highlight more on the PCIe switch implementation. But what I would like to highlight, what I would like to say is here, no, not this. So in the below table, I want to, explain about how PCIe bifurcation logic works. So why I would like to say is because this is a main functionality when PCIe is implemented as a switch. What do I mean by that is in the bottom, I have a physical layer which has 4 PHYs like PHY 0, PHY 1, PHY 2, and PHY 3. And each one are X4 configuration. And on the top, I have a controllers. As I've shown in my first diagram, the controller acts like a brain and it talks to the application logic. So the topmost row is a link. The first one is X16 link, X8 link, X4 link, and X4 link. And I have a different mode selection. So what do I mean is like, irrespective of any mode selection, I'm operating at X16 link configuration. So what do I mean is like, if I turn on all the PHYs and operate at mode 4, my output would be like X16 link configuration. Now, if I want to turn off Phi 1, Phi 2, and Phi 3 to save power, and I will be turning on mode 3, and then the output still would be an X16 link configuration. In the other scenario, like I would like to turn on Phi 0 and Phi 1, turning off Phi 2 and Phi 3, and operate at mode 2. So what happens is it grabs 0 to 7 lanes from X16 link and then 0 to 8 from 8 link, and still operates at the X16 link configuration. So there is a added flexibility here. You know, this is what like very important to understand when we are talking about the switches. When next slide is, you know, I would like to touch upon the implementation side here. So I have in that picture, I have a single monolithic SOC, and it is surrounded by subsystem implementations. So in this kind of implementation strategy, as a backend engineer, we would like, we generally have two subsystem implementations. One is a north-south and east-west orientation. We need to design in two different formats, and each one has its own challenging. So here, PCA's switch has three main functionalities. The first functionality is data routing. What it does is it makes sure that the data packet transfer between the devices are more efficient. And the second one is a bandwidth aggregation. So what does it mean is like all the devices which get connected to the PCI switch, you know, bandwidth aggregation happens, and then like there is a high-speed data transfer happens between all the connected devices there. And scalability, what does it mean is like we have a CPU, but with a limited connectivity and connected to the PCIe. But using a PCIe switch, what it does is it makes sure that it collects all the connected devices and gets connected to the single. So CPU is not limited by the pin connectivity. So that's all about the scalability. And here, before moving on to the next slide, like when I talk about multi-link subsystem, as I showed in my previous table, I have X16 link, X8, and X4 link. And I explained that I would like to always operate in the X16 link configuration. So here I have some implementation challenges in this kind of floor planning where all the files are stacked vertical, and I have a controllers which are sitting on the right side. And this is called as a rectilinear cut. When we have this kind of implementations, we generally end up with you know, standard cells like which are spread. I mean, standard cell is not uniformly placed. They are spread all across and causes cell density and congestion issues. It's fairly complex to implement such kind of subsystem. And the other subsystem like north and south orientation subsystem, here, if you see the white area, those where the standard cell can be spread uniform, this implementation is fairly straightforward, but it has its own complexity because we are dealing with thousands of clocks here. Thousands of clocks. So yeah, so the subsystem which east-west is getting implemented on the right, east and west, and the subsystem on the north-south will be implemented on north and south.
Time, okay. Like let's switch to like the challenges that you can explain, and then we'll conclude the session. Yeah, you can just touch on.
Yeah, so so this is my last slide. So I was already like, you know, talking about the implementation challenges. The first one is subsystem implementation. You already, most of the time it's like a macro dominant, IO dominant, and we are talking about millions of gates, standard cells being used. So fairly managing it is very difficult. Bringing up with a floor plan which is more you know, reliable, and then fitting into the SOC environment is kind of challenging. because they also come in the weird shapes, implementations. And then generally, like when I talk about implementation in the rectilinear shape, I already touched upon, like the standard cell placement here, is not uniformly spread. It adds an additional kind of, when you route the design, additional net delays, it adds the congestion hotspots, and then the timing closure becomes very difficult, and we need to have pipeline register for the timing closures. And we have to come up with effective strategies for the timing closure here. And then about CTS thing, right? We build a clock tree, and like generally subsystem would have like hundreds and thousands of clocking structure. It's always a custom clock tree built to achieve lower latencies and better skew numbers. So it's again a fairly challenging, and at the end, like it's a IR drop and timing closure to the SOC level. So the final will be like once I come up with a subsystem, it plugs into the SOC. Now SOC, it has to function according to the SOC standards, and the IO timing should be like met. So it has its own challenges. So these are my this is my last slide. Any question? Yeah.
Yeah. Today we'll conclude with the final slide. I'll just show the next generation interface solutions for the AI infra. So earlier we were talking about PCIe Gen 7 at 128 gigabits per second. So that standard was ratified like mid this year. At the same time, in a different room, PCIe SIG announced like a PCIe Gen 8, which is operating at 256 gigabits per second, which is double that of like PCIe Gen 7. So we are expecting that standard will be fully ratified in 2027, and then like people will start using it. And if you look at the ultra accelerator link and Ethernet, currently it is at like 224 gig data rate, 224 gigabits per second data rate, and these two standards will be moving to 448 gig by 2027. And there are like some additional security features also introduced into these standards. So if you look at the die-to-die or the UCIe protocol, right now it is at 32 gigabits per second, and it is transitioning to like a Gen 3, which is at 64 gigabits per second. And not only, I mean, this is mainly for like 2D applications. In addition to that, we have to look at like multi-die options and the 3D and 2.5D applications, where we are looking at like 3D IOs and the 3D compatible like UCIe IPs. This concludes our session. Thank you.
Thank you, Fani, and thank you, Rajesh.
AI's mission and what we would like to see from OPI is a part of all of these AI networks and components. And I would argue 802.3 is the 224.48 transition and not VC. We see some certainly protocol and minor physical layer efforts that are being pushed in IEEE.
Yeah.
So UEC itself doesn't actually push that transition or linear pluggable logic or things like that. But that aside, what of this ties into OPI and common APIs, common lifecycle information, common application use cases, especially on accelerator offloads? How do you tie your whole presentation back to OPI's mission?
Yeah, I mean, like, see, all these interfaces are highly programmable based on our bandwidth requirements. We can come up with the specific configuration, and that will help us tie into the OPI, the main goals. So, for example, like as Raj explained, like if you're looking at an accelerator, you can have like a by 16, I mean 16-lane configuration of a specific protocol, or like if you're looking at the switch configuration type of thing, like wherein you'll have like hundreds of lanes. So these are like modular designs and can be configurable based on the specific use case. Most of these protocols, that's how like it will fit into the main goals of the OPI.
So it's suggesting that the place that we can take OPI is into the system bus and system bus and component chip configuration at the system level, as opposed to worrying about, putting stuff on DPUs and that.
I did not get the last point. Like, yeah.
So what OPI's done so far is said, given a data processing kit, which, Vincat showed our diagram that defines kind of the envelope of what a data processing kit is on the very first slide. What are the things that can hinder the way applications could be commonly loaded across multiple vendors in the implementation of that or architecture, despite, variance in, how many architectures or how much you're building, which things are separated in hardware, which things are not, and all of that. So OPIs have the mission to provide the common APIs with that infrastructure. OPI has not really ever said we ought to tackle correct configuration of the IC interface, other than where they touch use and the virtual functions that are DPUs on PCIe and things like that. So are you suggesting that a place to take OPI is into the multiple types of high-speed interconnects that are especially being leveraged by AI systems, and that there's value there and an interesting commonality given all these different standards of the different commonality of doing that?
Yeah, I mean, our main interest, as I mentioned earlier, right? You all were talking about the application layer and like how the system can be used in like in the real scenario. The interfaces that we were discussing here are like needed for like a DPU and the accelerator designs. Those are being used within those designs. So how this particular DPU can be like, leveraged at the system level based on that requirements, like we can use like all these interfaces. That's what I meant. These are like the key ingredients needed for the DPU and the accelerator and GPU designs, the back end.
And I'm just trying to understand and see how that relates back to what,
So I have.
Well, every DPU has Ethernet. They have Ethernet. They have Ethernet IP, and everyone has a roadmap and they tell you which data.
Sorry, 1 minute pause. No, it's okay. It's okay.
That's my question. Because now, if you say, well, accelerators will have all these interfaces, and they ought to be configured in a plane, maybe that's interesting.
You want to use mic for the online audience?
So.
Yeah, good.
Yeah, so, the question is there an interesting type that we want to explore?
Okay.
Or what's being said here that does a few things. One, it expands the scope of OPI a fair amount, but it also maybe gives OPI another reason to exist, in that common ways of setting up these things across GPU server vendors maybe there's a place to go, except that the counter to that is all of the people involved in all the standards that are behind these nice colored boxes on the right, all think they're doing that internally and don't really want something common that's known the way across all of those things, either the hardware or the protocol level. At least they haven't historically in the history of the industry. There hasn't ever really been that. It's something to think about. Right.
Yeah, I was wondering the same when they're actually discussing this, like how this ties to OPI. So here's my take on that. So for UAL, I think OPI doesn't make any sense. But for UEC, maybe things like programmable congestion control on the interface can be configured via OPI to the NIC.
Yeah, but certainly OPI can configure those. The challenge you have there is that, of course, UEC has an entire API group. So that's defining all the APIs to configure over Ethernet transport protocol as well as the INC. There's an entire work stream, an entire group within UEC that's defining those things.
Yeah, right. But if we are
I'm really sorry, Vijay, because of time, we are already running 25 minutes late, kind of a thing. So I'm really sorry, Joe. So we'll continue. We cannot compromise on the lunch time, right? So we'll move on. We'd like to thank both Fani and Rajesh for the call. Thanks a lot.
Thank you.
So our next speaker is Narendra. He's a principal architect at Panasonic Avionics. So he'll be talking about software-defined vehicles and DPUs, one of the use cases of DPUs in software-defined vehicles. So welcome. So Narendra Atmakuri from Panasonic Avionics.
Hi. Can you hear me? Yeah. So, my name is Narendra Atmakuri. Currently working at Panasonic Avionics as a principal architect. Earlier, I worked on building the autonomous driving stack, where I would like to touch upon how DPU can be adopted there and how this autonomous driving stack would be get beneficial from DPUs. And the aspects of DPU in this aspect. So a brief about me. So I have worked in building the Galaxy phones at Samsung, and I also worked at companies like Qualcomm, Samsung, Broadcom. And at Aptiv, I was working at building the autonomous driving stack, where we were working on building the adopting the software-defined vehicle platforms, where we see a lot of computing power is needed. And the real world impact is like how you can do the more compute resource optimizations and bring the AI-based and ML-based perception stacks, and how better you can perceive the environment and take the right decision in the perspective of autonomous driving stack. And currently, I'm working on building the new modernization stack for in-flight entertainment and connectivity and networking. And I spoke at a lot of events related to software-defined vehicles and a lot of new technologies. So traditional, I'll speak a little bit about how software-defined vehicles is evolving and how it can be related to DPUs and the needs for high computing power and need for the offloading the infrastructure activities. So you see earlier in automotive industry, where you used to have hundreds of ECUs and a very complex way of interconnecting that, and the actual computing is very computing is very like it's distributed across many small ECUs. And now you see the shift, like where from the hundreds of ECU to a central computing unit, or you can see HPC, high performance computing, where it wants to have a zonal wise and make the centralized processing so that it can process in a better way and reduce the overall complexity and overall weight, and the easily manage over the software upgrades and a lot of new cloud native technologies and make it in the more maintainable and easily scalable. So the market transformation, you see it's going to be reached by 80+ billion by 2030. And you see in a vehicle overall cost, the software cost is going to be more than 40% of the total vehicle value. Architectural evaluation in automotive industry is going to be like a ADAS and autonomous driving all the way from level 2 to level 4 and level 5, and digital cockpit, connectivity and telematics. All this needs a very high computing power and a mixed criticality kind of the architectures, where you will have a parallelly running safety critical and non-safety critical applications running in a same computing environment side by side. And key enablers for this technology is like a sensor fusions, AI/ML perception, real-time operating systems with a high determinism, and hypervisors, containers, and cloud-native technologies, and adopting into the automotive safety standards. So I see DPU is a kind of the third computing pillar, where you will have a multi-core CPU with high performance network interface and flexible accelerating engines for AI and ML and security and storage. And it is actually complementing the computing models of CPU, GPUs, and specialized in a data movement and infrastructure offload. And a lot of critical capabilities that we can see, like open vSwitch accelerations, RDMA transport, GPU bypass, TCP offload, network virtualization, precision timing, and security operations, storage operations, and smart NIC integration, where you can see programmable data plane while freeing the CPU and GPU resources. It is used for the critical functionality like determinism behavior, and make it a resource available for CPU, GPU for the other things that it needs to do. And market momentum, I see major vendors like NVIDIA, Intel, AMD, Marvell driving adaptations across hyperscale data centers. Very brief about OPI project to accelerate DPU and IPU adaptation. To prevent a vendor lock-in. And I see like 5 working groups, make it a more independent underlying part of it, and develop is a more programmable and isolate, is a aggregation independently intelligent subsystems rather than directly coupled, and make it as a more decoupled way. And strategic objectives is like use the network storage, security, and cloud native infrastructure to develop the DPU devices without a hardware investment. Automotive relevance is like the, I would see like OPI standards architectures can be applicable to software defined vehicles, as automotive is adopting to the data center technologies for in-vehicle computing. So the relevancy for this technology and automotive. So I would say these are the key pointers, like architectural alignment. Modern vehicles are generating like 5 to 20 terabytes of data daily, and from sensors, and we need a data center class of processing capabilities, and offload and acceleration, where you need a DPU to offload a vehicle to cloud communication, and the sensor data processing, and a lot of network processing, and network security management and storage management, and real world validation. So this calorie MPPA DPU is already deployed and got some kind of the good results by deploying a DPU in this aspect. And security, so this will enable a zero trust security architectures with doing a lot of security processing, which is offloading to DPUs. And cost and power benefits, you see, power reduction and consolidating the functions and DPU reduce overall system cost by around 30 to 40%, and while improving the functionality. So just a brief overview on automotive AI workloads. Edge intelligence powered by DPU acceleration. We can see projected KPIs. In automotive, we need a very deterministic and time-sensitive operations would happen. Examples are like autonomous system computing to be able to break or understand automatic emergency braking feature. It should understand, and there is the time required is very, very less, sub 100 milliseconds time frame that it should be able to respond, and perception stack optimization. So where I see ML models and DPU style acceleration can improve the object detection accuracy and identify the environment in a more efficient way. And you see heterogeneous computing. So DPUs can be seen as a complementary to existing GPU-based AI training, and a lot of things like the data ingestion, pre-processing, and the data movement between performance domain to DPU domain and all, and scalability and flexibility. So it can see like easily we can use OTA updates and the AI models and algorithms without hardware changes, supporting a continuous improvement in the field and throughout the vehicle life cycle. So this is a brief about zero trust security. So we can see zero trust principles, like DPUs can play a very good role to actually enable a zero trust principles and completely offloading or taking care of the security functionalities all the way from the establishing the root of trust and all the way at security at each level. And cyber security aspect, like where V2X, OTA updates, and cloud connectivity, third-party applications, inline security processing. So you see DPUs can perform IPsec, TLS encryption, decryption inline at a line rate without impacting the application's performance, and enabling end-to-end encryption for vehicle communications. And this is also enables isolation and segmentation, where DPU virtualization capabilities enable a micro segmentation of vehicle networks that will enable to run a different networks and different networking segments within the vehicle environment. And you can have a safety critical ADAS functions, and from infotainment systems, you can separate and running all the critical and non-critical side by side. So this is automotive adaptations. How it can be done is like the safety relevant advancements like ISO 26262 and environmental robustness. So you can see in a vehicle environment, we wanted to have an environmental robustness and a real-time determinism, where you see automotive workloads demand a guaranteed worst-case execution time and bounded latency. DPU architectures must support a real-time scheduling, power and thermal constraints. So I would see some of these more specific to automotive requirements, and this should meet, to consider all these. I would say phased adaptation that can be seen like a apply this adaptation in a non-critical environments like infotainment and connectivity area, where it can slowly adapt it to ADAS acceleration and safety critical integrations. So I would see building a future together, how it is relevant with OPI goals. I would see, join a OPI working groups, contribute automotive use cases, and think in the perspective of how it can be adapted into automotive and non-extended as a avionics, in-flight entertainment aspects, and use case and developer platform working groups to ensure standards address SDV needs, and a developer reference implementation. So create automotive specific DPU reference architectures for demonstrating a sensor fusion, AI acceleration, and zero trust security for autonomous driving systems, and cross-industry collaboration. So bridge a data center and automotive communities through joint workshops, proof of concepts, and the standards between OPI and a lot of automotive standards like AutoSAR and SOFI. So I would see accelerated pilot deployments. I would see, comment as vision for 2030, standardized DPU architectures, become a foundational to software-defined vehicles, and a seamless interoperability across OEMs and suppliers, and accelerate innovate cycles, and reduce the development cycles from long cycles in automotive to months, and build the safer, more secure, and highly efficient way of offloading the infrastructures, and build the systems that will continuously improve and mobility experience to the billions of people worldwide. So any more details? My contact details are there. Thank you.
We'll do a quick question or we have lunch. No, a very innovative thinking, right? Is there any cost analysis that you have already done? This is very, detailed already, but if not, I think we should talk offline.
Cost analysis.
In the sense that, yeah, I mean, maybe two questions, right? One is cost analysis of what else is being used because automotive is a very cost sensitive area and DPUs are, as volumes pick up, maybe, we'll get to those numbers, right? So that's one.
So I would see in terms of the cost analysis. So as a overall, the value that it is bringing versus how it can be adapted into the bigger automotive product bill of materials or the overall cost of the automotive platform, I would definitely see kind of the very, good use and cost will overall make it a bring down overall perspective, the functionality that it is bringing and the way that it is being used to build the futures like the virtualization and micro segmentation and the mixed criticality applications. So earlier, there is a lot of software cost to improve the technologies and where we can see offloading this all to the DPU kind of environments where we can see lots of cost saving. So I would see the cost implication as the hardware cost versus the overall engineering cost and the software cost. So I would see a good benefit in adapting to this where you can have a lot of offloading to the hardware and bring this software functionality very cost. You see engineering cost, NRE cost are so high in this space and the cycles of the automotive cycles are very long. So those are all going to be very good impact of bringing all those to the capability to DPU and offload the infrastructure. You can decouple on the software stack and make it a more portable software modules that highly help the software industry.
Thanks a lot, Narendra. Really appreciate your presentation. Our next presentation is from John from Excite Labs. So he'll be talking about achieving 800 gig performance with Sonic Dash DPUs. Welcome, John.
John Carney, I'm from Excite Labs, and I'm going to talk about how we were able to achieve Dash data plane performance at 800 gig using DPDK. And so what I'll do first is I'll talk a little bit about what is Sonic Dash. I know some of the people here know what it is, but I think I'll review that. And for people who don't know what it is, I'll explain that. And then I'll explain how we implemented Dash in DPDK. And then I'll go through some of our 800 gig performance results for Dash. So what is Sonic Dash? So Sonic Dash is a Linux Foundation project started in October of 2021 by Microsoft. It stands for Disaggregated APIs for Sonic Hosts. And what it does is it defines the stateful host networking services that are the services that the hosts use in the cloud. And it enables a broad set of technology providers to create performance, power, cost optimized implementations. So if you think about the history of the services that are run in the cloud, they've used data planes such as OVS or VFP. These are sort of primitive operations, and the SDN controllers can link together those primitive operations to create services. But over the decade and a half of using those data planes, what's emerged is really a set of well-known, well-defined services that where we can now define the services and the APIs, and we can really optimize the performance of those. So instead of building the service on top of these primitives, we're defining them in a way where implementations of those APIs can be optimized, especially by using DPUs. And the idea is really to extend the success that Sonic has had for the stateless networking features or services in the cloud to the stateful features that the hosts use in the cloud. Here's an example of Dash on a smart switch. So first I'll say that Dash can actually, the Dash data plane and Dash could actually run in many different places. It could run on the host itself. It can run on the NIC in the host. It could run on an appliance. It could run in a smart switch. And there's some particular value when it's actually not running on the host. I'll talk about that a bit. So in this diagram above, you have your servers. Those servers have CPUs and NICs. Typically, that server may be a bare metal server where there's just a single tenant. That tenant needs to be isolated from the cloud infrastructure. That server may be running VMs. There may be multiple tenants sharing those VMs on that server. And typically, it's the NIC where the SDN policy is applied, where there's security, isolation, billing, those kinds of features are running on the NIC. But what that requires is that that NIC be capable of handling those services at the performance and scale required by the workloads that are running on that server. And there are workloads that may exceed the capabilities of that NIC. For example, very network intensive, very high connection rate kind of workloads, like sort of network function kind of workloads. And so that NIC might not be sufficient to be able to handle the SDN policy and enforcement for those workloads. So the idea is that you could run a data plane disaggregated from the server on a DPU, for example, in the smart switch. And in that case, traffic would be tunneled. So if you look at the server on the right and the VM on the right, traffic would be tunneled through the NIC to that DPU, and all the host services would actually be implemented for that VM on the DPU rather than being implemented or executing in the NIC. And you can have a mix. You could say some VMs that have modest workloads, their services are being applied on the NIC. Other VMs that have very high, high connection rates can be run on the DPU. The other benefit of this is that you could develop new services that may not be implementable on the NIC. It may be some legacy servers and NICs, and if you develop new services, those can be developed on the DPU, and they can be offered to the tenants that are running on those servers and on those VMs. So we'll take a look at one of the services of Dash. There's about 7 services defined for Dash, but sort of the most basic service and the one from which all of the others sort of extend is called the VNet to VNet service. And so for the VNet to VNet service, the data plane has to apply several lookups and transformations on the packets. They have to map the overlay network of the tenant to the provider's underlay network. The Dash data plane has to do stateful connection tracking for both TCP and UDP connections. There's a requirement that Dash perform 5 access control list operations per connection setup. Data plane has to also do accounting for billing. It also enforces bandwidth, packet rate, and flow scale limits. And one of the very important things that the Dash data plane has to do is it has to synchronize state from one instance of a Dash data plane to another instance of a Dash data plane for the purpose of high availability. So that if a link goes down, if a DPU fails, that from a tenant perspective, there's no loss of connectivity. All of their connections in the network will stay up and continue to run. And now if you take a look at what a dash data plane has to do at 800 gig performance level, there's very high scale requirements. It has to support 12.8 million outbound routes in the route table, 128 million ACL prefixes, 32 million mappings, and perhaps the heaviest requirement of the scale is that it has to support a connection table with 128 million active flows in it. This is enormous scale. This scale of these databases requires many tens of gigabytes of DRAM. And that's challenging for any kind of dash implementation because what it means is that really in order to process packets in the dash data plane, it just requires many, many accesses to DRAM. There's no ability to rely on caches or locality for performance. And in fact, we'll talk a little bit later about the testing. And the testing specifically is done in a way to make sure that any implementation of Dash can handle this scale, assuming that there's no locality. This is a look at a diagram of the Excite Labs Dash DPDK software architecture. So the gray boxes are hardware, and the blue boxes are cores. In our case, they're ARM cores. If you look at the hardware on the bottom, there's the NIC, or in the case of our DPU, we call it the E unit. Really doesn't matter. What matters is that the hardware provide a POLMO driver, a DPDK POLMO driver for interfacing to the Ethernet, the network. And then on the top is the memory system. And the memory system is where the databases live, where the flow tables live, your counters, rate limiters, packet buffering. And then the software is in the middle. So in our architecture, there's a control core that's responsible for initialization, for some periodic sort of things like stats collection. And then there's the gRPC server, and this is where configuration from Sonic or from the libsci comes into the data plane. And then there's a series of cores, worker cores, and this is where the main packet processing happens in the Dash data plane. And then that's scalable to as many worker cores as you can put. And then there are aging cores, and the aging cores are really doing some background processing where they're looking at this connection table and they're deciding whether flows have been idle for an excessively long amount of time, and they're basically recovering the resources of that connection table for flows that may have gone idle. Perhaps the endpoint power was disabled, something happened at an endpoint, and you have to eventually recover those resources from the flow table. And in our architecture, aging is also something that's scalable. You can apply multiple CPUs to this aging process. Some key attributes of the Excite Dash architecture is that it's platform independent. So we didn't implement this Dash data plane to only run on an Excite DPU. We implemented it as a platform independent application. We've run it on x86 servers. We've run it on ARM servers. Of course, we run it on our DPU. Another attribute is that it has linear performance scaling. If you can put N cores on the application, you get a certain level of performance. If you put 2 N cores, you'll get double the performance. And finally, this is a very simple programming model, and I'll talk about that a little bit more. But the idea that we had was that we wanted to keep the DPU programming, specifically our Dash data plane, We wanted to architect it as something that was very simple programming model. If you were to look at the code, it would make sense. It would be understandable. So a little bit more about the programming model. So we make use of the hardware's receive side scaling logic. So the RSS basically performs a static hash over the inner 5 tuple. This allows us to finely balance the overlay flows to CPU cores by looking at the inner 5 tuple. All packets in a flow are processed by the same worker core, so the RSS is essentially pinning flows to cores. And it's a simple run-to-completion processing architecture with proto-threads. So what does that mean? So in software data planes, there's lots of different architectures, different ways of batching and pipelining and doing different things. But the run-to-completion programming model is really the simplest. It's a way of thinking about you receive a packet, you do linear processing on that packet all the way to the completion of that packet. Now, with such high-scale databases, if you were to use a run-to-completion programming model, what will happen is typically you'll stall on your DRAM accesses. As you go to do a route lookup or you go to look in the flow table, any kind of memory access will stall because it's not in the cache. And so we employed something called proto-threads. I think that this is kind of unique that we took something that really wasn't designed for data plane programming, and we applied it to data plane programming. But it's a very lightweight threading infrastructure that's stackless. And what it allows us to do is at the point in the code where you may stall on a memory access, we can issue a prefetch instruction, and then we can yield. And that will then allow another proto-thread to continue processing. And the other proto-thread itself had yielded on a memory access. And by the time that proto-thread is able to run, that latency to memory has already been hidden by the other proto-threads running their logic. What we found with using proto-threads is that we can maintain this very simple programming model, and it doubled our performance. Then we also have aging cores, and the aging cores are continuously walking the flow table, and they determine if the flows have exceeded their configured idle time. Now, one of the important attributes of Dash is that if you set an aging time on a flow, you want it to age out, if it's been idle for that amount of time with some, amount of accuracy. So for our implementation, if a flow has an age out time of say 30 seconds, we'll always age that flow out within 200 milliseconds. There's a sort of 200 milliseconds of uncertainty around that 30 seconds of when the flow will be aged out. And that's not that easy to do. I've talked about memory latency, memory performance quite a bit. And for a DPU or for any kind of other kind of CPU architecture, this can really be what limits the performance of the application. And so DRAM throughput, latency are limiting factors. The more DRAM access capacity the platform has, the better you'll be able to perform well for the Dash data plane. It's critical that the data structures that are used for the Dash data plane be specifically designed and optimized for Dash. If you don't do this, then you may do a lot more memory accesses than are really required for the data plane. I'll give you a couple of examples of this. Dash requires 5 ACL operations per connection setup. you could imagine some generic ACL algorithm and you just call it 5 times. That may not be optimal. It may be more optimal if you exploit the fact that it's 5 ACLs that use the same 5 tuple. Start to think about how you might be able to optimize your ACL algorithm for being able to do multiple searches with the same 5 tuple. Also, the scale of the rules. And you can think about how to optimize your algorithm around the very specific scale requirements of Dash. Another example of this is in the flow table itself. The flow table is actually what dominates the memory footprint of this application. And if in the aging process you have to visit all of these flow entries, that's a huge amount of memory bandwidth to visit all of the flow entries in the flow table. So again, if you design your data structure specifically for Dash, you could take the information in the flow entries that's critical for aging, and you could separate it out from the rest of the flow table entry. And so now, for example, if that critical information is 1 byte, you could read like a 64-byte cache line from memory and be able to get the aging information for 64 entries at a time. And you drastically reduce the amount of memory accesses that you have to do, for example, for aging. So I think, the key takeaway here is that you can't get to the highest performance for Dash without actually designing the algorithms and the data structures to be very specific for Dash. And then finally, in the design of those data structures, if you can minimize the memory footprint, you can actually reduce the system cost. So for example, most Dash data planes would require somewhere between 32 and 64 gigabytes of memory for 200 gig worth of scale. And we can do 800 gig worth of scale within 64 gigabytes of memory. And that's because we're able to optimize the size of those data structures specifically for Dash. So final slide here is I'm going to talk about our test performance. And there's something in Dash, there's a definition of a test called a hero test in Dash. It's really designed to be a stress test. It's really designed to have lots of packet traffic from different flows, again, so that you can't rely on any kind of cache locality. And so the test requires that you have background traffic for 64 million UDP flows, connections, and then you have 60 million TCP background flows. And while that background traffic is running, you have to start and terminate new connections at 12 million connections per second. Not only do you have to do 12 million connections per second, you have to run at 12 million connections per second for 100 seconds without dropping a single packet. And that's challenging because any kind of instantaneous load could make you drop 1 packet. So over the course of 100 seconds and many billions of packets, might not be that too hard to drop a packet, but this test requires that you have 0 drops. And so when we took our Dash data plane to our testing partner, an independent testing partner, they ran the hero test setup using the Ixia CloudStorm traffic generators. And then on the right, we had what's our DPU evaluation platform with the Excite DPU. Let me just say one thing about the Excite DPU. The Excite DPU, you could think of it as a very energy optimized server SoC with integrated networking and accelerators. So it's a very software-oriented DPU. It has 64 ARM Neoverse N2 cores, and that's the chip that was in the platform on the box on the right. When this was tested, we ran it with 52 worker cores, 2 agent cores, and 1 control core, and we actually achieved 14.3 million connections per second, exceeding the requirement by 19%. And we did that, again, without dropping a single packet. That leaves some remaining cores for running the Sonic control plane, or you can do anything else with those remaining cores. And in addition to this, we've spent some time looking at this data plane, and we believe that we can achieve an additional 25 to 40% improvement with further optimizations. So with that, I can take questions. Christina. Yeah. So I'll summarize what Christina just said. Christina basically said that there's a real business case behind this technology that what would have taken maybe many VMs in order to get the connection scale can now be done with a single VM because that SDN data plane is now capable of handling the workload that was really running on that VM. So instead of the workload being limited by the SDN data path, now the SDN data path is really scaled up so that the workload can run on a single VM. Is that? Right.
It's an online question. What's the ratio of NIC to dash, and how many NICs can a single dash?
So, I think that, the typical use case of dash is in a smart switch. Like the number of links or the number of ports like connected to the switch, I think can really be flexible. I mean, in the case of the E1, like we support 2 by 400 gig E. So in a smart switch, you'd have 2 400 gig links to the switch. But the fact is, you could be 8 by 100. It doesn't really matter because the traffic gets balanced across those links and then gets processed by the dash data plane.
Yeah. So we can talk all day about prefetching and cache lines, and I've been doing this for a long time as well. My real question then is, what does it mean for OPI? Similar to like 2 presentations ago, that question was raised as well. Are you saying we should do this, like we should expose dash, or what is the real message for OPI specifically, right?
Yeah, I mean, I think, one thing is to just, one sort of overarching thing is just, here's another workload. And it's a workload that's, of interest to cloud providers. It may be of interest to enterprises eventually. These services are services potentially that all hosts need. And yeah, how do you roll this out in a way where an enterprise type customer could run this on either DPUs, right? Host attached, or maybe, there may be more discussion in OPI about other instances of DPUs, like DPUs that are, switch attached instead of host attached. Because I think that there's a much broader set of use cases for DPUs than just DPUs that are directly attached to the host.
Thanks a lot, John. Really appreciate it. So our next section is more close to my heart. It's about 5G UPF offloading and in a real commercial environments. We have Shiku Hirai-san, research engineer at NTT, and Katsuma Miyamoto-san, deputy manager at NTT. Over to you.
Okay, thank you. I'm Katsuma Miyamoto from NTT Docomo. I'm in charge of reading the architecture of 5G core network at NTT Docomo. So today we would like to introduce our proof of concept where we implemented 5G core UPF function on DPU cards and connected to our commercial network. And we also integrated with AI solution. It will be introduced by Paul. So, okay, let me briefly explain about 5G core network. Yes, so NTT Docomo is one of mobile operators in Japan. We launched 5G services in 2019, starting with 5G NSA. And so then we also launched 5G SA in 2021. So as of today, over 30 million users enjoy 5G services with 97% population coverage access across Japan. So 5G core network is positioned between radio area network and the internet. So it not only handles the user traffic, but also realize the function like session management and authentication. So in 5G core network, as you can see, there are multiple network functions like this. And so today we would we focus on the UPF. UPF stands for user plane functions that is handle user traffic. So in order to handle the user traffic, the GTP tunnel is used in mobile network. So for downlink, which comes from the internet to user equipment, UPF receives the IP packet from the internet. It's encapsulation with GTP and send them to the G node B. On the other hand, UPF receives the GTP packet from the G node B. It decapsulation them and send them to the internet. So in order to handle the GTP tunnel, UPF have to communicate with SMF to receive the session information. And UPF also has various functions like this, such as QoS, packet counting, packet reporting. Yeah, that is unique to the mobile network. So because of this, so we have been exploring UPF implementation on DPUs. So the detail will be explained by Siku in the next part. But the ARM CPU on DPU handles the PFCP processing and slow pass as well. And the network processor on the DPU is responsible the fast path between G-node B and the internet. So by implementing the 5Z UPF functions on the single DPU, it could be ideal for the edge use cases. So we call it this UPF. We call this UPF distributed UPF or DUPF. So so Shiku will explain the detail of the implementation.
Hi, I'm Shiku Hirai from NTT Docomo. So I was a member of NTT R&D until September, and now transferred to the Docomo's core network design department. And so I'm in charge of design and development of Docomo's commercial 5G core networks, same as Miyamoto-san. So I will talk about the distributed UPF. We call it the UPF on DPU. And this is the detail of our DUPF architecture on Bluefield 3 DPU developed by NTT R&D. So UPF slow path is a container running on Bluefield 3 ARM cores. And UPF slow path is responsible for the data plane session control, cooperating with the control plane functions of 5GC through the N4 interface defined by 3GPP standard. And UPF slow path uses PCP as a communication protocol via control plane functions of 5GC. For the control of data plane session, we called UPF fast path. We are using mainly Dockerflow API. And main tasks required for UPF, such as GTP encap, decap, and QoS processing, are processed at the connected 7E switch integrated into Bluefield 3. And our new UPF can be combined with some value-added functions needed in the telecom networks, such as IPsec. Both UPF slow path and more intelligent processing can be launched not only on the ARM cores within the DPU, but also on the host side CPU cores. We aim to enable the selection of the optimal configuration based on demand and requirements. For example, in use cases requiring large-scale requirements or more advanced computational processing, we believe it is appropriate to launch on the host side CPU cores. On the other hand, when small scale or limited functionality is sufficient to launch on the ARM cores on the DPU side, and that full DPU offload architecture is appropriate. And NTT R&D have started a collaboration with NTT Docomo since last year to challenge interconnecting the UPF and Docomo's commercial 5GC and LAN. We contributed and exhibited our DUPF at Interop Tokyo in June this year. Interop Tokyo is the largest internet industry showcase in Japan. And at this event, we performed the experiments to connect DUPF to the Docomo's commercial 5GC and LAN, and verified several scenarios. As shown in this diagram, only devices with dedicated SIM cards were actually accommodated in the DUPF. And LAN and 5GC functions other than DUPF were running on the commercial environments, actually accommodated the other general user devices. And the video streaming and LLM services previously hosted on Interop Tokyo have been provided to devices with dedicated SIM cards through the DUPF and Docomo's commercial 5G networks. And this shows the system rack overview at Interop Tokyo. And our DUPF server hosting Bluefield 3 cards is here. And so at this time, so we supported two key features for interoperability with commercial networks. The first is that UPF must follow notifications of user session state changes from SMF. SMF is one of the 5G core network functions and responsible for the management of user session statements. And so we supported the dynamic control of flow rules on DPU to follow changes in user session statements. So this enabled various procedures such as handover and incoming call with packet buffering. So we tested the handover procedure while connected to the actual commercial networks at Intel of Tokyo. And the second is filtering things. So we supported the filtering specific user packets on DPU. This enables SDF filters for local breakout to the MAC and charging operations. The SDF filter is rules defined in the 3GPP standard for granular traffic control on a per user basis. And we tested that specific packets could be locally broken out to the MAC, while other traffic could be routed to the internet side. And also, we integrated our DUPF with F5 products and services to validate future AI native network architectures alongside several use cases. These slides and videos shows some example. For example, model routing based on language identifications and assistance of LLM response by using system prompts. And also application of security policies against prompt injections. However, so there are still remaining issues for commercial applications. For example, we need more complex user level flow configurations. For example, we need the QoS and charging rules per user basis. And of course, monitoring, observability, and redundancy are the essential for telecom network. So we need we need those supports in the future. And finally, so let me to express our expectations for OPI from the operator's perspectives. So the first is we require vendor agnostic APIs to control merge vendor DPs. So at this time, we used previously, but we are open and also interested in other vendors' DPUs. So we hope that dependencies on each vendor's SDK will not be required and cared. And the second is long-term support for DPU-based platform and solutions. So we also expected the creating ecosystems and for long-term support for DPU-based platform and solutions. I would appreciate it if we could continue to discuss on these and other matters in OPI communities. Thank you. I will switch also.
Thank you very much. So I'm going to start by saying, so my GitHub handle is PDB2shirts, and I'm going to be wearing two different shirts here today. One is an F5 shirt, one is an OPI shirt. So start from an OPI shirt. How is this relevant to OPI, and what does it mean for OPI? This POC and this solution, it's actually out in the market. This solution in the market is relevant to OPI because Balazs in one of his, early in his presentation, talked about big IP being one of the next workloads that we wanted to run on a DPU. So this is I'll show you here in a minute. This is a solution that runs the big IP traffic management microkernel, the core of our big IP platform, on a DPU. So we're getting to that next level there. This solution is, from an OPI standpoint, about where we were 2 years ago when we were building Nginx solutions and running them on DPUs. Quite a manual process. Wasn't the place where we could take and deploy that workload across multiple DPUs easily at this point. So that just to set the stage, that's where this solution is as far as OPI. It's in we've proved that it will run on a DPU, one type of DPU. Now it's up to F5 and OPI to work on how do we get that to work across the industry of DPUs that are out there, DPUs and IPUs. So that's my OPI hat. That's where this presentation fits with OPI. Now to put on my F5 shirt and talk a little bit about what we've done here and how we've done it. So so the names are changing here, and I'm not the marketing guy, but is Big IP next for Kubernetes on a Bluefield 3, or you've also saw it's changing to Big IP next cloud native functions on a Bluefield 3 DP. I mean, it's a product name from, I don't know who made it up, but it's a long product name. Anyway, what does it do? It runs our Big IP core system on, we've ported it to ARM, so it will run on an ARM architecture, and we're currently validated running on a Bluefield 3. What does it do? Some of the things that this does tackles a multi-tenancy problem, and I saw in some of the other sessions that that's an issue, especially in the automotive session. I thought that was an interesting tie-in, where in the automotive session, the tenants were a safety secured area of the functions that needed to happen, and then a more infotainment session. So our solution here is an ingress and egress solution into a Kubernetes environment. It gives us the ability to tie Kubernetes namespaces back to data center networking constructs, be it VLANs, VXLANs, BGP, those sorts of things. So on whatever you're using to move traffic and secure traffic and segment traffic within the data center, this solution keeps track of namespace to that outside data center networking object. So now Coke and Pepsi can co-reside on the same cluster. They can use the same AI cluster. We can segment and multi-tenant that cluster and use the Big IP to keep that traffic separate. Namespaces keep it separate within Kubernetes. Our product keeps it separate in the data center networking space. So together, it's a full multi-tenancy solution. Yes, we've got rich observability, and we can do some fine-grained traffic management. One of the things you also saw was that very similar to what we did with the early Nginx demo, where we had Nginx running on the DPU, and we had an AI workload running on the host. We're doing the same thing in this demonstration. We're running the Big IP traffic management microkernel on the DPU itself, and then sending that traffic securely to an AI. In this case, it was an AI gateway or an AI guardrail solution that did prompt injection security and that sort of thing running on the host itself. So that's what we did there. I'm getting the shepherd's hook. So I think I've got one more slide, but I will just cruise to it. The other thing to note here is that throughout this session, we've seen several other workloads that are running on DPUs. So the distributed UPF is a workload that runs on a DPU. In this instance, we're running 2 DPUs in a host. One's running the distributed UPF functions, and one is running the Big IP functions. We've seen Nginx running as a workload. We saw the automotive stuff running as a workload. We saw Dash running as a workload. So I'm heartened that it's not that we're seeing, from an OPI perspective, we're seeing multiple workloads now running on these cards and being seen as valuable to customers, such that they're spending money to buy these workloads that run on these cards. So again, did you guys have any extra slides, or was this it? This is the last slide? Okay, this is the last slide. So I think with that, I can stop and ask if there are any questions. And if not, we'll go from there. And I think it's maybe lunch? No, something? Oh, one more session. One more session. So, any questions?
Just one question on the. So, has speed practice any source code implementation, or it's the UPF is any like any open source code implementation, or it's
Basically, our in-house solutions. In our in-house code.
Yeah.
Can we bring this to one of our blueprints in OPI?
Yeah, I think that's the next step is taking this solution and seeing how we put it in OPI and how we make it work across multiple vendors' cards. And I'd really love to see how do we make it easily deployable as well across those cards.
In your setup with 2 DPUs, which is also something we're looking at, it's maybe like a prerequisite for this, I would say.
It is right now just for the power required,
Okay.
the processing power on the cards. So maybe if we had a different card in the lab that had more power to it, we could do it on one.
And then a more detailed question here is then the DUPF is on one, and then does it talk through like hairpins out, or how do you cross from DPU to DPU, or do you go through the host?
It's house, yeah. So he just said it was outside. So it's a networking connection from one to the other.
Okay, thanks a lot. Thanks, Paul. Thanks, Shikoira-san and Katsuma Miyamoto. So we are on to our final session. In fact, it's the most important session for quite a few, all the OPI members who are here, and also for me, for my job. So this is about the role of the OPI. This is a panel discussion. I would like to invite first Swati Mittal, who is our member and the software architect at Intel. Swati. And we have Vipin Jain, who is a senior fellow at the AMD. And I'm really thankful for him to agreeing, accepting the invitation and joining this panel session. And we have Tim Michaels, distinguished engineer from FI. Please welcome them to the session. Over to you, Swati. So she's very well prepared with the questions. Good luck.
For programmable platforms. Been working with the OPI for the last 2 years, and we've delivered several blueprints to the OPI. And what we're going to talk today is the heart of OPI, like Sridhar said. We want to know how do we evolve OPI to keep it relevant going forward. And when we talk about OPI adoption, 3 areas come up: blueprints for DPU offloads, lifecycle management, and fleet scale orchestration. And we have 2 leaders, Tim Michaels from F5 and Vipin from AMD, joining us to share their insights on this very important topic. So with that, let's dive right in. Blueprints for DPU offloads, lifecycle management, and fleet scale orchestration. All 3 are critical for us to go forward. But if we think of OPI adoption as a maturity journey, where does the foundation need to be strongest first? What has to come first? Lifecycle management, offload APIs, or fleet orchestration? So the goal for me today is to take back, what do you think as the next set of immediate priorities that OPI should invest time in? Vipin, do you want to go with that?
Sure. I'll just say a few words. I am working on I worked on the DPUs. I'm working on the AI products at AMD, but that's about me. I'm a coder. So to your question, if you can't bring it up, you can't do anything with it. So of course, you just make sure that the baselining, which is the life cycle and all those things, are easy. Otherwise, no matter how great you are, it's not going to go any further than that. And you can promise, moon and stars, but that's going to be pretty much the first bottleneck that you need to handle. And I think looking at all the demos and all that, I think OPI has done a decent job. There are a few things that have been lined out by people that we need to attack and look at. Nevertheless, I think that is the first priority. Second, immediately the second one goes into, which is a little bit orthogonal because this is to enable people to use it. The second one, which is like blueprints, because that attacks the use cases into the heart. And I'm so glad presentation from Panasonic, presentation from on the Sonic stuff, presentation by other customers on how they are deploying, various ways in which they are looking at DPUs. So blueprint second, and the rest.
Tim, what do you think about it?
Yeah, I think life cycle is a big word and it covers a lot. So I would say the part of life cycle, which is the out-of-box experience, is the most important thing because this is the first time somebody touches a DPU and tries to do anything with it. And if they get so frustrated, they just put it back in the box and ask for an RMA number, then we've failed, right? The industry has failed. So getting that sort of, and we talked about this, having some guides almost per card about how do you onboard your new card for this vendor A or vendor B or vendor C. And we've had some blocks there with vendors not wanting us to use their NDA material. So we've had to sort of redact some of the stuff. But that's key is to at least tell people, here's a way to do this. Come follow our guide. There's a light here to shine on how to get your card up and running. Then the next step is, well, okay, I finally got my card. How do I provision it, right? How do I get it off of the base software it was shipped with? And I'm very excited to see, Fusion Layer stepping in and starting to look at those workflows. We looked at those 2 years ago or longer, and we had some initial ZTP stuff in place, but I think that has atrophied a bit. So I'm glad to see them coming back with some new energy. And that's part of the blueprinting is saying, hey, how do I get this first step done? I get my out of box and then I get my initial software stack installed. All right, and then you're on to the next piece. And this is we won't get anywhere if we can't solve the next piece, which is even if you get a few cards installed, and you get your base operating systems there, how do you now get your workload on there? And how do you do that in an efficient way that's going to be automatable and eventually scalable? And so this is where the DPU operator, right, comes in. This is showing people how you can deploy workloads, how you can do, your classic, deploy one workload, kill the other workload, move across the infrastructure. This is what's going to be needed, for at scale deployments of DPUs and workloads. I'm also excited again to see Fusion Layer giving us the alternative because there's a whole class of enterprises that are not ready for Kubernetes. As much as we don't want to say that, they are not. They want to deploy bare metal. They want to deploy VM-based applications. I think Fusion Layer is showing us a really good way to do that. And they're very complementary because they're addressing different parts of the market. And then only when you get that, and somebody's like, okay, I'm doing pretty well with 10 cards. Now I want to go to 1,000. Oh, we got a whole new lifecycle management problem, fleet management. So how do we get the telemetry piece, the observability piece, to let them do that? And then lying under all of this is this fear that before I buy 100 or 1,000 cards, I'm afraid of vendor lock-in. And I'm afraid of evolution over time from the Rev A card to the Rev B card, from Gen 1 to Gen 2, from vendor A to vendor B. Show me how I can move my workloads over time and even potentially run heterogeneously. I can leave my first 100 running on Gen 1. I can deploy a new 200 of Gen 2 and keep it all working as 300 cards. That's what the customers really want. And they're not seeing that from the industry, so they're hesitating, right? Those are my comments.
Right. The customers are not seeing it. And I agree that we have to first build, life cycle workloads and then fleet. That's the order that we ideally want. But we all vendors know that every time we engage with the customer, the first question is, show us the value prop of the use case, right? So that's where everybody's focus goes on. You spend all the effort in trying to show you the throughput, latency, performance. And the fleet management does not even happen until the very end. So at OPI, our challenge here is, first we're trying to get all the blueprints to show the customers our value prop, and only then we can go to lifecycle management. If you see today, most of the DPU vendors have a use case that's working fine, Maybe it can scale up to a few hundred cards, but I haven't seen a fleet management solution that can do thousands. And if you talk to data center owners, most of them will say, since who are actually transitioning from a NIC to an IPU, they would say, oh, we would use our traditional fleet management, which basically would just have like a Dell iDRAC or something to just monitor your thermal, power, temperature kind of things. So the question really for OPI is, if we have to attack really only the first provisioning, right? And then the offloads and the fleet management, what would you see as a provisioning infrastructure in mind? What do you have in mind? Like, do you have examples you can share that we can link to OPI and kind of build a blueprint around it, or suggestions on that?
No, I'll speak based on my interactions and contributions in OPI probably a few years ago. But there was a very good set of discussions on how the DPU can have a very tighter integration using the standard APIs with the server PMC. And I think we should not try to, like everyone is saying, let's not reinvent the wheel. There is no reason to do that, which means if folks are okay, I'll step back. One thing that I learned being in the infra business for 25, 30 years is that there are people whose jobs depends on your products. They are not going to take a risk and shake up the whole world just because you are so awesome. It doesn't work like that. So which means that, whatever they have it working, you have to align with that. And the way they work is because they have all the tooling in place and they have all the software to manage these things and everything in place. And so aligning with that, trying to have a server discover the DPU, trying to have a server establish a trust relationship with the DPU, server BMC, do that is a very natural way, in my opinion, for existing deployments to take leverage and take advantage of those things.
Yeah, what I was thinking when you were talking, Swati, was the challenge we're really up against here is how do you give birth to an ecosystem, right? So we have the vendors, they're having a lot of success, in fully bespoke implementations with hyperscalers and even telcos. Where we're struggling is this broader ecosystem that addresses the whole industry, the whole enterprise data center space. And there you need not just DPU vendors and not just customers, you also need these ISVs, right? You need the people who are going to bring the apps that the customers will buy to run on their DPUs. Some sophisticated customers can bring their own apps, but the bulk of the market says, oh, I want to run a routing stack. I'm not going to write it, right? I want to run a firewall. I'm not going to write that, right? They have these use cases, so it's good to see stuff like UPF, but we only have a handful. We need that scope of library of applications and vendors supplying and supporting them to get much bigger before we reach a tipping point. So, and it's been slow. I would have hoped where we are today, we would have been at 2 years ago, right? It's been very slow. And AI has caused this huge, sort of shift of attention away from this space. The space hasn't left though. It's still here. It's just not getting much attention right now.
Right. So actually, okay, even if we reuse, Vipin, to your question, even if we reuse the existing BMC mechanisms to onboard the IPU using DHCP or SZTP, whatever is appropriate, the next step is once we get into the workloads, we've got two questions. What workloads do you see are immediate for OPI for standardization? Right, that's one. And second is, how do you actually provision those workloads? Because that'll include all those APIs that we're talking about. So can you kind of highlight some of the workloads that you're seeing are being commonly used, are most popular? Maybe they are more popular due to AI or have a significant impact on the AI infrastructure, and that's where OPI will stay relevant and can invest time in it.
Okay, let me go first. Isn't it fun to be sitting in between you and your lunch, I think you talked about there were demos that described various use cases. Provisioning using Kubernetes seems nice, natural way to start to not just bootstrap a DPU, but also start to load so-called packaged applications to be deployed on those devices naturally. So it seems more natural to go that route. wherein people don't have to like deal with any idiosyncrasies of the device in direct way. They can just continue to write their NF or network functions or some other applications that could be deployed on the DPUs. So that deployment model sounds decent way to me.
Sure, yeah. How about for like P4 programmable platforms where, say, you have a customized pipeline, right? How do you actually enable the customer to download a customized pipeline program specific to that workflow?
Yeah. I think it's a very important question, and I think in a hallway I was talking to someone, and at the end of it, if people don't see the value coming out of it, then they will always question, should I even go with DPU or should I just go put a standard NIC and offload a few things and be done with it? So coming to your question on P4 based customized pipelines, and we have been building P4 NICs since 2017, I guess. And we have had tremendous success on building products using those pipelines. And I would say that it does bring the value for specific use case. One thing I would say is that implementing your own P4 data path on a DPU should be decoupled from the deploying of an orchestration and onboarding and life cycle of the DPU itself. Once you get the DPU going, what program you're running, it could be the network load balancer that you want to run there. It could be something else. Who writes that program should not be tied to exactly someone who is directly doing the actual deployment, rollout, and orchestration of the DPUs and all that. So first answer was about like, how do you get DPU into the general purpose things? Now, when that part gets instantiated, are you leveraging the capabilities of the device? And if device gives you a way to do more than maybe flow lookup, do you want to take advantage of that? That's where I think, some of these things that you mentioned where bring your own data path logic comes in. If you do not need your own data path logic for that kind of acceleration, great. Just use the ARM cores and you're good. But if you do need that, then there is a possibility of how do I bring my own data path into DPUs? And for that, I think you have to look at like what kind of compilers and what kind of P4 data path support vendors have. And I believe that at least Intel and AMD are definitely working on the P4 based DPUs and NICs. So that standardization, I don't know whether it belongs in OPI, but we have that going as well. But I think, it should be along those lines. It's like I've squeezed 80% out of the ARM cores. Now, how do I get it to do 2x or 3x of that? That's when they have to look at whether it's worth investing into building your own pipeline, because you own that pipeline. As a vendor, AMD does not know what you are doing there and how you are taking advantage of proprietary innovation that you want to bring on those DPUs in the data path. So that's a call someone can make at the point when they decide to say that whether investing certain amount of resources would be worth it or not. Big people, big clouds and all that, they're perfectly okay with that. They're happy investing a team of engineers trying to squeeze that every ounce of the processing power that is given in a DPU. The business is built on that. They will do it no matter what happens. But the question here really is that how would a common developer do it? And for that, I think they need to look at any acceleration device, and I don't mean to say it has to be P4 because I'm working on building a P4 NIC. It's okay. Every device has certain capabilities. If you want to go beyond the basics of deploying the DPUs and all that, I believe someone was having a presentation saying that let's do offload first, then go to acceleration. So this comment, the second comment I have on the P4 goes into the acceleration bucket, not in the offload bucket.
Yeah, I think that was Balazs that said that. And I think there was a good point there that there is a place for OPI to work on abstraction of accelerators. We've touched on that in the past. It's quite difficult, and it requires a lot of sort of vendor interaction of reconciling offloads that are similar but not quite the same. And so I think we've kind of set that aside, and we have more focused on the deployment of the offload onto the DPU and the ARM complexes, and let's solve that problem. And when that's working, then we can try to solve this. So we sort of pushed that problem into the deployed application. That application needs to know how to tap those accelerators, and we're not giving them an abstraction layer for that yet. I think that's a to-do down the road for OPI, definitely. That would be on my list of things we should tackle. But in the interim, I think, and it's a measure of maybe why DPUs have struggled, is that the power of the compute in the DPU is still kind of anemic computationally. And so a lot of the value ends up looking like SmartNIC accelerators, and then people are like, oh, I'll just run it like a SmartNIC. Well, I don't care about those ARM cores, turn them off. Why did I pay for those things anyway? I think when we look, though, to the next gen chips that are coming, they are significantly more powerful computationally, and I think you're going to see that needle move. And you're going to see offload applications that don't need to lean on the hardware accelerators yet actually be effective, because now there's going to be enough compute to make it happen. So I'm excited about that.
No, I was going to say that I want to dispute, and this is a discussion, of course. I want to dispute a little bit with him here. It's, I mean, you can add more compute by adding lots and lots of processors, general purpose processors. DPUs were built to do I/O, and I/O really, really well. Why not take advantage of that? And I kind of contest that, it is that's when the value will come out. Otherwise, you will keep building bigger and fatter devices that people will always question, wait a second, why am I paying so much? Why is it consuming so much power? This NIC consumes like, 20 watts and you are here. Why? What is it that I'm getting? And this question will come back and forth. If you build a domain-specific processor for an I/O domain, take advantage of that domain. Would you ever use GPU to do standard things? Never. Would you ever use CPU to do matrix multiplication? Never. Then why do you want to use DPU to do standard CPU work? You can use CPUs. I mean, AMD is building a whole bunch of cores, yet they acquired Pensando. Why? That is because that domain is better served for a class of applications that requires a heavy amount of I/O. So when you say that there is plenty of compute that's going to come, it needs to come in both forms. It sure enough, I mean, there is general purpose processing needed on the DPU. I agree with that. It needs to handle the scale and all that. But yet, if we are not appealing to the domain of an I/O, then DPUs are going to become irrelevant in mind of a customer. I don't say from the vendor point of view. Well, that's my take. Question. Oh, why don't you give this?
So when I made that statement, I think the important word was first and second. I'm not saying let's not do accelerators. I definitely see the value, and it's always been the case that first we go from general purpose, then the needle swings to offloads, and then swings back because the general purpose is more flexible, and the ASICs become better, and so it goes back and forth. It's about priorities, because if today we had 5 times as many people sitting here, we would be doing accelerators already, right? It's literally that. Like, it's about figuring out what do we do first and what do we do second.
Yeah, it's interesting if you think about, because I look at this stuff doing our architectures, the system on a chip CPU architecture where they're adding accelerators around the CPUs and making them sort of a computer on a chip, basically, right? And a DPU, if you take the right view, they look very similar. So what distinguishes a DPU? Well, it's this idea that we want to have compute and accelerators close to the wire, right? And we want those functions that apply to the wire to be right there. And we want this separation of concerns that we want to get those things off of the main CPUs for latency reasons, for compute offload, for security reasons, right? But we're not seeing all of the things we would hoped we would see. We see the networking, but where's the security? I don't see a lot of NVMe and things like that we thought maybe we would see on DPUs. Maybe people are doing it, but it's not coming to OPI, right? Yeah.
Yeah, the other way that I see it, Vipin, to your point, is it's not just the cores on the CPU. It's also like an infrastructure offload. The cloud service providers, the consumers don't have to know what is running as an infrastructure offload and consuming their cycles, which is like the base case used for IPUs. So just having a lot of cores on these on the host server is great, but you want to monetize that as much as possible and offload to the cheap IPUs, right? So not everything is just can be done on the cores, right?
Okay, I had lost my mic too. But yeah, no, I think there are two parts. I think the reason people still wanted to do things in the, on the course on the DPU was because they wanted the separation between tenant and the cloud. And so for that reason, you cannot just use the host CPU. So we get that use case. The cloud use case is very clear, multi-tenant cloud use case especially. The VMs running, you don't trust anything running up the host. Fair enough. But then when we talk about, and I'm glad that, out in this room, everyone is associating themselves with DPU more than OPI right now. I mean, I saw more presentations on how they associate their use case with DPUs. There was Sonic Dash presentation, and every presentation after another, the question was like, how is it relevant to OPI?
And that's what we're trying to figure out here.
I know,
Which
I'm
of
bringing the
those shall
point
we-
back. I'm bringing the point back to that, which is like, everyone is wanting to use some way of accelerating these devices, and they're calling it DPU and equivalent. Like a smart NIC is what we used to call anything that does more than RxTX on a device with RSSDSO and basic stuff. That's the classic NIC. Anything more than that, that is doing smarter stuff, does it belong in OPI? Maybe, maybe not. But those are the use cases everyone here is associating with when they come here and talk about their DPU related use cases. And to me, I was actually very thrilled to see that people are seeing DPUs in places at least I never thought they would discuss. Like in a car, I was like, this was the last place I thought a DPU would be considered to be deployed. Again, I think people are considering it because they have a use case in mind, because that ecosystem is evolving very heavily, and they need an interoperable way to work on those things. But I think it's a good thing. I didn't mean to say that one is less important versus the other. All I was saying is that ultimately user will see a value in using a DPU if it does more than what a classic processing unit can do. Because otherwise, it's like, okay, I have another board that does the same things that the CPU board does, and you should use this as an acceleration device. Okay, maybe, and that'll become questionable in someone's mind. Why am I paying X amount of dollars for that? And by the way, these cards are not like, super cheap cards. I won't comment on the prices, of course.
Thanks. The other one question that I had was, it's more about security and trust that comes up with the DPUs, right? And its model changes with the AI infrastructure that we want to build. So if you want OPI to be the foundation for a secure AI infrastructure, what does trust need to look like operationally, right? Is it about establishing the hardware attestation first, or managing the software identities and APIs consistently across the vendors, right? How do we make it like OPI is AI certifiable, right? The trust is there in the OPI framework.
I'm not sure I have a response to that.
Yeah.
I can take that. I mean, being a vendor, I'm close to how the bootstrapping happens at the board level and all that. There are two trust models typically. A DPU or a cloud trust model is like, I'm not going to trust anything on the server. The network is trusted because that's where the cloud is accessing the infrastructure and trying to manage the tenants that are running up on those hosts. That's one trust model, wherein there is like a big red line between the tenants and the DPU. The other trust model is that I trust whatever is running in the host, and that's the AI use case you talked about. If my DPU is sitting on an AI cluster, the application which is running on the host is a trusted application. There's only one application running, which is doing inferencing or training. That's the only application that I'm running. So what's the big brouhaha about these things? Maybe I'm running multiple tenants on the same host, and maybe one tenant is given certain amount of GPUs, another tenant is given other ones, and so maybe I need to do some of that. But anyway, I'll come back to the trust model part again, which is that the trust model in some use cases, and I don't mean to say AI is the only thing that falls in that bucket. Most of the appliance use cases that people talked about may fall into that bucket also. The NFV or the software data plane or the UPF data plane, which is running in the user land, it's a trusted entity. It's owned by the infrastructure admins of the and the operators of the infrastructure. So that is not something which is not trusted. So in that case, the trust model for DPU is really to bootstrap a trusted piece of software and ensure that it does not veer away and loads any software that is not either certified or validated. So coming back to it, so in both trust models, first, identity needs to be validated. I think we have talked about in OPI community quite a bit about like how is DPU going to assert its identity to the rest of the system, and that could go to the BMC to the host, and it could cross-validate that yes, this server is trusted, and so the server is trusting the DPU, and therefore from that identity, validating that identity boots up the rest of the software layers. And I don't want to belabor this discussion about like how the overall bootstrapping of trusted software works on general operating systems and all that. So that remains exactly as is. We don't need to reinvent that. But the fundamentals go into like whether that identity is validated by the network or the identity is validated by something running on the host. And so either way, the mechanism to have that identity burned into these devices when they are manufactured to all the way to asserting that and validated to be validated by another entity on the board or from over the network is the API gets called from over the network or from the host, but the mechanism remains same in my opinion.
So do you see a scope for OPI providing APIs to make this consistent?
I think we talked about that.
layers?
Yeah, I think we talked about that. And that's where I think we need to work. If we want enterprise adoption here in OPI, we have to work with Dell's, HPs of the world, and Lenovo's of the world to make sure that these devices can be authenticated and can be asserted well in those things. I don't think we were able to do that in OPI, but I did that with VMware. With VMware, we released Project Monterey, and AMD DPUs were the first one to release that in maybe 2020 or something like that. But we did exactly similar things, wherein it is an entity that, host stack is ensuring that a trusted device exists and trusted device is booting. So to me, it's needed if we want enterprise adoption. For others, security is never a bad thing, don't get me wrong. It's just that it's a non-starter in a certain environment, whereas it is good to have, and then all that option.
Thanks. From an AI infra perspective, do either of you have any, what do you see as, do you have something that you want to highlight that will be important for OPI going forward, other than what we've just spoken about?
From an AI perspective?
Yeah.
No.
Oh yeah, you bet. I think my diversion from the DPU was a little bit there because I started focusing on AI quite heavily, and rightfully so. That is a much bigger use case, or at least we thought so back then, and maybe we were not wrong. But like everyone here, they associate a smart entity, which is not part of the server, but in a card, that needs to have a standard way of running, operating, and managing, right? There are probably 3, 4, 5, I don't know, AI NIC vendors. AMD is certainly one. They announced a Polar product last year. And then Broadcom announced Thor in OCP. I don't know how many of you heard that. And I'm telling you that there is another product. And these are like 400 gig, 800 gig devices I'm talking about, right? And then not Broadcom, the NVIDIA, of course, has that. These are 3, I know, big ones, but there may be other ones too. Please pardon me if I'm ignoring, mentioning a product. But these are smarter entities. And the reason I say smarter entities is that when AMD releases a product, they're not calling it a NIC. They're calling it AI NIC. When Broadcom releases it, they call it, Ultra Ethernet NIC. And when NVIDIA releases it, they call it, Super NIC or something like that, right? The common theme here is that there is a smarter entity which is doing more than the standard NIC. And I believe I had asked the question, what's the role of the backend, things in the previous panel. I don't know, Paul, maybe you mentioned that, it has to do congestion control, it has to do modern transport, it has to do all these things. These are not simple stuff. This requires implementing like TCP-like congestion control in data path, in network. So obviously we are not talking about a very simplified entity. This is a smart entity that is trying to do a whole bunch of things for AI. And rightfully so, everyone who thinks that, OPI started with some smart entity that needs to be standardized, then yes, it belongs in that. Now, what part, honestly, I've been contributing into UEC, and I'm part of the UEC discussions on a weekly basis. And we talk about like what kind of things are needed versus not. If not here, we'll go standardize it over there. Of course, there's an RDMA stack and all the host interfaces that are being defined, drivers being written, and all that. There are elements in OPI that we should talk about, like what can be done and standardized over there. First model, bootstrapping of the devices, all those things. Right now, they just assume that it's going to be all vendor driven. I don't know whether OPI needs to adopt it or not, but my feeling is that, if we chase use cases and if we chase customers, we will not get it wrong. That's the simple, thing. So AI is a big use case. I mean, obviously AMD is seeing it and AMD is betting on it, but at the same time, it's not hidden from the world. Sure enough, there might be ups and downs into how people think about AI and it's a bubble or not. I'm not commenting about that. My main thing is that there are people who are genuinely building these things that needs to have some way to deal with vendors. And like I said, there are 3 vendors. None of them is talking about, I'm the only one probably here, but none of us are talking about standardizing the use of AI NICs, or I'm not calling it AI NICs. To me, it's actually a DPU. It is a DPU in a different shape and form. Because it's a smarter entity that can do obscenely high amount of processing at a very high rate. I mean, I'm talking about 400 gig, 800 gig of data transfer, and this is highly stateful data transfer on one card. So, I mean, we talked about, 2x 400 gig on the appliances in Sonic. And here, sorry, Joe, you have a question? Yeah. Yeah. So this is the second.
So on your Polaric 400 AI kit, what would you want standardized?
I think, yeah. So I'll repeat the question. So basically, Joe is asking on AMD's Polara AI 400 NIC. That's the name of a product from AMD, which is basically allows interconnecting GPUs at a very high rate and all that. And I think Joe's question is, what do I think can be standardized there? Correct?
I asked, what would you like to have?
Oh, what would I like to have? Yeah.
Related to what you think could be standardized, not exactly the same.
Yeah.
So, because in OPI, we've had some trouble other than provisioning and a little bit of life cycle on agreeing to what shall be standardized. Because everyone has a different opinion about what should be standardized, so they don't match, and so you can't have a standard if you get Greek. So from your point of view, and AMD's point of view, on just one instance of a card, Polara 400,
right?
Because you just talking about
right.
AI and offload.
Correct.
That do a good job of what you do. All you guys who have that card do a good job of what you do. And I like them all, as you know. Question is, what would be OPI standardized? What would you like to see OPI standardized? That's the question.
Yeah. I think it's a great question. What would AMD like to get standardized in OPI for AI NIC use cases? Is that a correct question?
How would it
match up to what we have been doing? Oh yeah. Of course.
They like the same thing standardized. If so, we might have a basis actually do an additional set of these.
Correct.
All presentations today, you saw these things happen.
Yeah.
But we've been blocked many times trying to perform. When you were active in OPI, there were lots of contention over networking and how it should be done, and everyone said we went.
Yeah.
You guys did, everyone, we said we went. Dell said we went, sure.
Yeah.
So question is, so I'll let you answer the question now, but the context there is a lot of history of what we try to do. But I still think there's opportunity.
Yeah. I don't know. If you want to comment for the Intel, please go ahead. Yeah.
No, I don't have any comments on the Intel side.
Okay. Yeah. Of course, not on the Polara product, but yeah, anything that you have. I think the base part of the software stack on how the backend networks can use the RDMA function all the way from an equivalent of IBV layer, which is an InfiniBand equivalent of Ultra Ethernet. That part is being standardized in UEC. And we are talking about how those APIs will look like and how the drivers and kernel drivers are being upstreamed and software stack is being defined, how people will manage those things and all that. We can talk about whether this should have been OPI versus not, separate discussion. But that part is well covered from multi-vendor point of view. The things that we are not directly addressing is indeed security aspects of things. People are thinking, oh, it's a card. We have never talked about security of a card. But wait, there is a trusted software that you want to run on that card. Do you want to have a way this could be done? There is a talk about, and I think AMD released Helios, DRAC, and all those things, right? We are opening it up. It's a reference design. It's not directly a thing that someone has to take it. It's a reference design. You can take the reference design, build your things around. But if you go underneath, these are very complex set of pieces that are interacting with each other to establish not just the trust, but also the bootstrapping of the whole thing, collecting the information about what parts are going wrong. I believe someone was commenting that, in a large cluster of GPUs with hundreds of thousands of GPUs, 1 million GPUs, something is guaranteed to go wrong. I mean, every minute or every second. So how do you collect the failures from this thing in a standard way? There's no standard way there. I mean, I'm answering your question, hopefully. So there's no standard way to, people are talking about standardizing RAS and, those things. In OCP, there are some discussions. I don't know if OPI had some discussions on this stuff, but telemetry, we talked about it, but never had a focus on how is it going to work for these kinds of server deployments and all. Other thing is the bootstrapping of the devices themselves, just not the trust, but the validated images and software which is running on these things. Finally, if there is a data path code, you need to make sure that is also coming through the standard this thing.
Common bootstrapping, which we actually have some
Yeah.
So security config, common bootstrapping, common error collection.
Oh, yeah.
Okay.
All the RAS functionality. Oh, well, the last one I was saying was if someone wants to program the data path, it will fall into the bucket of maybe how you are allowing the common way to, okay, let me put it this way. There is a discussion on how the programmable congestion control needs to be happening in UAC. Which basically says bring your own congestion control, because everyone has different network and everyone has different requirements. They feel that they have got full control on how best to manage the congestion. I'm all for it. So I'm not saying that we will here we need to standardize what congestion control needs to be there, but interface for someone to provide their own transport and their own congestion control is something being discussed, and it's not standard. Yeah. So there are two aspects. The PCC, or the programmable congestion control, as discussed in UEC, we are heavily discussing what APIs will be there between the transport and congestion control mechanism. We don't need to standardize that in OPI. What I'm saying is that for a compliant PCC, how's that going to roll out in the infrastructure? No one's talking about it. It's a very clear thing that I'm telling you.
So my comment, Joe, is none of those things you listed, except maybe this very last one, is unique to AI, right? These are general problems that OPI has looked at. So when you say for AI, I say, well, not really. The things OPI is looking at are applicable to AI, but they're more generally useful to all the DPU use cases.
I want to add one thing to what Tim was saying. The reason it is different for AI versus the others is because the layout of a server, I don't know if you have seen an AI server. It's freaking massive. 7 tons of a rack. It fits 2 cars worth of weight. And the amount of components that integrates with each other in that one is different from a general purpose server. If you try to apply the standard principles of DPUs there, it will not work based on what I know, which is why I'm saying there is a scope for looking at that and standardizing it. Because the way components are laid out and the way they interact with each other is not exactly the same as server. Again, that's how I feel, which is why there is slight difference there that I think we could pick up there. But
Cards being targeted at AI workload, traffic acceleration, cards don't have quite as many general capabilities in general as a standard you would. And that means that the subset of the APIs you might want to define wouldn't be had broader chairs. I wouldn't run Nginx on for example, or on a CXA, or on a foreign print. But those cards have the characteristics we were just talking about, and there could be a benefit in the industry for a common API for a part of it, which is why I asked them the question. So you're right, there's a separation in card capabilities that matters.
So Tim, a follow-up question for you. So you're saying that AI is actually a separate chapter within OPI, and it's not like the umbrella charter that OPI has currently. And if you want to support AI infra as a part of OPI, it's actually going to be another type of support. It's not. Okay, thanks.
But these big systems he's talking about are mostly bespoke single vendor implementations where they're not looking for a standard. They're doing their own thing in their system. And even when they ask an OEM to build it, they say, this is MGX, here's how you build it. If you don't follow this, we will not bless it. And so even the OEMs are being told, you will build it in a bespoke way. I believe AMD is going down this path too of building bespoke systems. And until we see this sort of a AI cluster as a broader piece of infrastructure with dozens or more of companies building those systems, OPI's role there is very limited, I think.
I think it is an open invitation for anyone to contribute in. OCP is a perfect forum for us to discuss building these things. And OCP is actually standardizing some of these things as well. So the point I was bringing too is that, if you, obviously AMD as a company does not want to wait for a whole world to converge on something and say that. The idea behind reference system was that, it is not the only thing that will exist, of course. If we want to build something like that, it's telling that these are the components and it's opening up and saying these are the ways they interact with each other. Now, if anyone or others are building those things, sure enough, there is a way to plug in components from different vendors and make it more generic. And of course, at the benefit of the end user, try and reduce the cost.
I have a question. So CCLs are used in AI networking. So AMD has RICL, NVIDIA has NICL. So it'll be good to have a CCL part of OPI so that it becomes a standard, especially for communication across nodes using the CCLs.
Yeah, I think it's a maybe a little bit of orthogonal discussion in the sense that SYCL, we call it XCCL or SYCL, is really dependent on how GPUs are exchanging data amongst each other. And if we always devil is going to be in detail, if you go 2 layers down, certainly you'll realize that every mega cloud has their own SYCL layer. They don't use NICL, they don't use RICL or anything like that. Which is okay, because how you want to leverage the models, because ultimately communication depends on how model is creating the data exchange between GPUs. And that is very specific to a model, and many big guys do not have open models. These are closed source models, which means the way these models offload the task to different GPUs creates a way for what communication patterns exist between them. And so trying to say that we want to standardize it, we need to know those models in this room, and I don't know whether we are well equipped to do that, to be very fair. We could attempt that, but I think it's better left out to these guys to say, hey, you have a transport, RDMA transfer, you want to use it in any kind of communication collective, whether it's all to all, or all reduce, or whatever that communication collective is, and whatever innovative way they want to do it, let them do it, maybe.
The problem is CCLs are different.
Yeah.
And they aren't really tied to an infrastructure offload element in any general way that you could then propose an API. CCL sit above all the cards. Cards is what will control the software of the cards. CCL really sit above that. If there was specific configuration for transport, carrying the traffic, mobile news traffic, or whatever. We talked about that. That is a potential place. You wouldn't want to have OPI try to go. That because those are already sort of functions. Those are already top things that have their own universe. Just like you wouldn't really want OPI to go get involved with the UEC configuration.
Right.
That already has its own full effort, as I was saying.
Okay, thanks. I think Sridhar is saying we're almost out of time. If there are no questions from the audience, anybody else, I would like to thank our panelists for their views and insightful, comments. And I think what I understood is we have a lot of use cases that that are DPU related, and we do want to bring them into OPI. So we've got to we want your support to bring those use cases to us so that we can have the blueprints that we can show to our customers. And you can in fact tell your customers that it's at an OPI lab where they can view and see how it's working for their own. And that'll help us strengthen various use case APIs. And so we're looking forward to hearing back from each of you. Thank you.
Thank you. Thanks, Swati. Thanks, Vipin. Thanks, Tim. Thanks a lot. As Vipin said, we are really now between you and your lunch. So thank you. So that brings to the conclusion of this excellent OPI Summit on DPU and IPU. I would like to thank all the speakers and all the attendees who have joined us. For the speakers, I have your photos. You can collect it from me by paying $10 kind of thing. Let's go for lunch. Lunch is right there. So let's have it then. Thank you so much.